Okay, we're going to declare that the numbers are settling down a little bit. I can't actually see the numbers, but everybody else can. So that is good. I am really glad to welcome you to the first day of our Trustworthy AI for Environmental Science Summer School. I'm Amy McGovern. I'm the director for the NSF AI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography. And we are co-hosting this summer school with NCAR. And so I'm going to give you a quick overview, but mostly going to talk about logistics before we get going. Assuming that this Zoom thing works here. Okay, here we go. So we are the NSF AI Institute for Research on Trustworthy AI and Weather, Climate, and Coastal Oceanography. We are one of the NSF AI institutes that was funded in 2020. We are led by OU. All of the other academic institutions that are involved are on here: Texas A&M, Corpus Christi, North Carolina State University, Colorado State, University at Albany, University of Washington, and Del Mar College. And if you want to learn more about us, I would recommend you go to our website because we have a tremendous amount of information out there, and I don't have time to give you my usual overview talk. I'm giving you a 2-slide overview just to tell you what we're doing and why we're running the summer school and why we're very interested in creating trustworthy AI specifically for weather, climate, and coastal oceanography. So I'm starting with who's involved. I've got all of our academic institutions. We're also partners with NOAA. NCAR is involved, and then we have private industry who is also involved. So Google, IBM, Disaster Tech, and NVIDIA, we're founding private industry partners, and we have since added Park, Vaisala, and Radiant Earth Foundation. And you can find out more about all of them on our website. The goal of what our NSF AI Institute is to uniquely benefit humanity by developing novel, physically based, and what I mean by that is they respect the laws of physics, AI techniques that are demonstrated to be trustworthy and will directly improve prediction, understanding, and communication of high impact environmental hazards. And all of that is our mission statement. And we're going to be doing that this week in summer school. We're gonna be talking about all of those. We'll be talking about physically based AI techniques, XAI specifically. We're gonna be talking about what it means to be trustworthy. That's a lot of what today's focus is, and how we can improve the prediction, understanding, communication of all of these high impact hazards. So this is my, as promised, very short overview of TAI4ES. This is only slide 2 of my overview. So we have 4 foci that we work on. 3 of them work together: the foundational research in trustworthy AI and machine learning. And you'll be hearing from some of our people, but we also have talks from people who are not involved in TAI4ES this week. Everything we're doing in our foundational research in trustworthy AI and machine learning is inspired by the environmental science applications. So we have 5 environmental science application domains that we're looking at: convective hazards, thunderstorms, tornadoes, wind, lightning, wind, hail, winter weather, coastal oceanography, tropical cyclones, and seasonal to subseasonal prediction. And then everything we're doing is hand in hand with risk communication and social science researchers, where they're actually examining what it means to be trustworthy and trying to figure out why our AI might be trusted, why it might not be trusted, and what we can do to improve our AI, and so that our end users actually care about and use and trust our AI. And we're going to talk a lot about that today, what it means to be trustworthy. The final focus is not to be number 4 because it's last. It's just number 4 because it doesn't fit in that cycles, but it is very much key and part of what we are doing. And that is that we are working on workforce development and broadening participation. And those 2 go hand in hand. We've been developing an AI certificate at the community college level. We're one of the first in the nation that have an AI certificate. We thought we were the first in the nation, but there I think are 2 deploying this fall with the workforce development in the community college level. Ours is focused on AI for environmental science. It's being held at Del Mar College, and a lot of the classes are online. And if it's very successful, we're hoping to take it nationwide to get more people involved in AI at all levels. So by looking at the community college level, we can reach out to high school students because they can do concurrent enrollment, as well as people who are returning and retraining from the workforce. All of that together puts us into our NSF Institute. And now I'm going to transition, keeping an eye on my time. I'm transitioning to what we're doing here in our logistics. So I want to say we have about 1,300 people registered. I don't think we have all 1,300 people logged in yet, but they will get there. As you are, some of you are just watching live stream, but there is on the live stream link, there's a Slido link, and I have a graphic so that you can get into the Slido if you're not in there already. It'll be coming up in another page, but we wanted to point out that we are committed to providing a safe, productive, and welcoming environment for all participants. This is UCAR's statement of code of conduct. TAI4ES has a code of conduct that is very much in line with this. I put this whole statement up here so that you understand that we are committed, and anything that shows up on the Slido is moderated. And so there will be nothing that is not safe, productive, and welcoming showing up in the Slido. And if you want to read the full code of conduct, it's linked on the website as well as right there. And there we go. I promised that there was the QR code for Slido. It will be on this slide and the next slide, so you have a chance to scan it if you're not already in the Slido. All the talks are, these are just sort of logistics. All of our talks are going to be broadcast live, so they are being broadcast right now. There's about a 20-second delay between what I'm saying and what's going on the live stream. So we speakers will be trying to watch Slido and take into account that delay. You can put your questions in through the Slido, so go scan that QR code and get into the Slido. The chairs for the day will moderate the questions and we will read them to the speakers. So for those who haven't used this kind of setup before, what's going on is the speakers for the day are in Zoom, and then we're live streaming out to the web link that you got. But it's only the speakers that are in Zoom. So we don't have the usual sort of Zoom chat and all of that. All we have is the Slido. So we'll be moderating the Slido and looking at the Slido and using that to do all the interaction for the day. Every day for the 4 days of summer school has a theme. The theme for today is trustworthy AI for environmental sciences, and specifically focusing on those first two words. What does it mean to be trustworthy, and specifically for AI? What does it mean for AI to be trustworthy? Day 2 is going to be focused a lot on XAI, or explainable AI, with of course the goal on environmental science applications. Day 3 is an ethical and responsible AI with a focus on environmental sciences, of course. And then day 4 is all case study work. Every single day is 3 hours. We kept it short. We know that this is 2021. We know we've been on Zoom and Google Meet and all these other things for a year and a half now. And so we wanted to make sure that you're engaged and focused and having fun, and we put in some short brain breaks. And so 3 hours is sort of our maximum for each day, so that we knew that you could have a lot of fun, learn a lot of information, and then we take a brain break, and we'll see you again the next day. The schedule for today, what we're going to do today, you're getting me right now. I am the introduction and logistics. Then we are going to jump into what is trustworthy AI. Then we have a short 5-minute break, and then we're going to do some examples, talk about how AI prediction has already been done in the field for hail and why it's trusted and why it's not, and then look at trust models for that, and then look at some other examples. So looking at AI prediction and understanding what the forecasters want for AI for severe weather prediction, and then looking at XAI for tornadoes. And then we wrap up for today, and then tomorrow's focus is a lot on XAI as well. I want to point out that our website, AI4ES.org, has a tremendous amount of resources for learning AI and machine learning. I will say that because there was a summer school last year that focused on just the foundation of AI and machine learning for environmental science, this year's summer school is focusing on the trustworthy aspect. We assumed that you had some background knowledge in AI and machine learning, so we're not jumping into the methods so much this summer, although we'll jump into a little bit of the XAI methods. But all of these educational materials are linked to from our website. So I took a screenshot there where if you go to the website and you click on education, you can get to all these materials, and all of them are freely available. You can watch last year's summer school, which is hosted from NCAR as well. You can watch, we've been running short courses. So a short course, the difference between summer school and short courses is the summer school is a bit more broad, and then the short course dives in depth into a project, into a topic. And the short courses that we have available have code for most of them as well, so that you can like dive in, look at a method, and then go try it out on your own data or the data that's provided to you. So go to our website and you can get a whole bunch of resources. And this is my final slide. I wanted to thank the NSF for funding us, and thank NCAR and UCAR for supporting us, and all of the team at NCAR, and Susan Dubbs at OU, who's been organizing everything, and all of our guest speakers, and all of you for coming and participating. And I think I am slightly early, but I am right on time to move us to our next speaker. So I will stop there and let Anne start sharing slides, and I will go check Slido to make sure there aren't any questions.
Good morning. Let me go ahead and share my screen. Good morning, everybody. Okay, is that looking okay, Tasia? Julie?
Yes, looks great, Anne.
Great. So today, Julie Demuth and I will be presenting on trustworthy AI, and we're going to talk a little bit about what trust means and what we're doing in this context. And I am going to start with a brief introduction, if I can get this to work. Okay, and I'm Ann Bostrom at the University of Washington. I'm a faculty member in the Evans School of Public Policy and Governance, and I've had the great pleasure of working on this project with Julie and her colleagues, and also with two graduate students, Ann Hoon and Hunter Smith, who've contributed a great deal to this project. Over to you, Julie.
Yes, thank you, Anne. Hello, everyone. I'm Julie Demuth, and I'm a research scientist at NCAR, the National Center for Atmospheric Research in the Mesoscale and Microscale Meteorology Lab. And Anne and I are co-leading the risk communication portion of the TAI4ES research that Amy just so nicely introduced. And also as part of our team, we have Mariana Keynes and Chris Wers, who are two brand new postdocs who are working on this project with us. So we definitely want to acknowledge their contributions to what we'll be talking about today. Thanks, Anne.
Great, thank you. And we are going to start with a poll. So if you're not in Slido yet, we'd encourage you to get into Slido and enter the code that's shown on the screen here. This is a poll on trustworthy AI and what it means. We'd like you to do this poll to start thinking about what we mean by trustworthy AI. And we'll give you a minute or two to fill out the poll. Tejak, if you could give us a cue when answers have started slowing down, that would be great. Thank you.
Getting everyone thinking deeply here right off the bat.
Yeah. For those of you,
we have 69, 74. They keep going up. We have lots of results.
Great. We'll give everybody another minute or so then. What do you think, Julie? So we were up to over 200 responses. We'll give it another couple minutes. That's about half of our respondents. Another minute or so, Julie?
I can see it going up. You're up to 283.
Oh, great. Okay.
Maybe when you cross 300. You just
Sounds
did.
Good. Excellent. Okay. Tasia, I think we will start looking at the results, but we'd like people to please take time to continue answering. And we'll try to track these results later to report out on them at the final recording. Okay, so results. Can we see some of the results now? Let's see, I can't.
They're showing up in the screen share. Can you see what she's sharing?
No, I can't.
You just get out of your full screen PowerPoint.
Okay.
We have to do that. And while Anne is doing that and is sharing the results, we would love people to be able to share kind of what you think about these answers. So think about what is kind of how people are responding to some of this, how they're agreeing or disagreeing. If you have any comments, go ahead and add those in the chat, or I'm sorry, into Slido.
And also I'd like to say, as we start looking at the results here, we're looking at the answer to the first question, that this poll was developed based on Table 1 and Jacoby et al.'s paper, and we will provide references at the end of the talk. This is a paper on formalizing trust in artificial intelligence, and they based their table on the formal European guidelines for trustworthy AI models. So we've derived these from the European guidelines, and we can see fortunately for the European guidelines, that people agree that this is an important constituent of trust in AI. And so we have about 56% agreeing that this is an important component. 57%, it's going up as we speak. And if we go to the next response, please. So that was the answer to the first question on whether humans can interpret what the AI model is doing. So that's interpretability. The second question is that the AI model outputs are accurate, reliable, and reproducible. And here we see not quite as much agreement. We see 48% agreement, and we see that 19% strongly agree. We only have about 32% disagreeing here. So still a strong agreement. We find, as we'll mention again in a few minutes, that accuracy is often a very important component of trust in people's discussions of the literature, at least, and in several of the studies that have been done experimentally so far. Should we look at the next question? Now here it looks like we have about as much agreement as we did on the first question. So the AI model has been developed on FAIR principles, fair data, findable, accessible, interpretable, and reusable data. And many modelers, at least, are very keen on this, that the data are a really important component of a trustworthy model. Julie, any comments? Or?
Yeah, I think it's interesting that on these first three items that we're getting about a quarter to a third of people who are disagreeing. And so that's interesting. If you have any thoughts on that, please feel free to go ahead and put them in Slido.
Yes, especially the question is, why would people strongly disagree that the model, that this would not be an important component of trustworthiness? For those of us who are worried about data assimilation and how that trains the models, this is an interesting question. Should we look at the next question? So the fourth question here is, the AI model has been tested extensively on relevant out of training sample data. And we can see here that we've got about half, 49% agreeing and 23% strongly agreeing. So we've got about 3/4 of our respondents agreeing that this is an important component. Only 4% strongly disagreeing, but still a quarter disagreeing that this is an important component of trustworthiness. The next question. And here we have the AI model is transparent. So transparency also is an important component in many people's minds due to accompanying explanations. So this goes directly to explainable AI, and we have different types of explainability highlighted here: saliency maps, influence functions, for example. And here, once again, we've got slightly under half agreeing and about 18% strongly agreeing. So not quite as much agreement as with the previous questions, but we have here 34% disagreeing, which is a little bit higher, and 1% strongly disagreeing. If you have comments on why this is, please put your comments in Slido in the Q&A. So far, I don't see any comments. Okay, and then the last here is the AI model and its application are sustainable, socially and ecologically beneficial. Very interestingly, this seems to have the strongest agreement of any of the questions that we've seen so far. So 57% agreeing and 24% strongly agreeing, so more than 3/4 of our respondents, and only 15% disagreeing as a component of trustworthy AI. So this is really interesting because sustainability and social and ecological benefits are not a part of many of the discussions of trustworthiness in AI.
Yeah, I agree. And so it will be really interesting. I encourage everybody to kind of continue to reflect on these and really kind of think about how your thinking on this might shift over the next couple of days, especially after today. Actually, Anne, I was thinking we should do a pre-test, post-test. It's really what we should do and ask these polls again at the end.
That would be fun. So I just want to highlight, based on the results we've got so far, it looks like this last question is the one that most people agree should be part of trustworthiness. And the first question that we showed, which is humans can interpret the AI model, is the next most. And then we've got the third, fourth after that, and the third and fourth questions also in third and fourth place. And then we've got the second question here, the AI model is accurate, reliable, and reproducible in the last place, as far as I can tell, which is kind of in contrast to a lot of what we see in the literature, as we'll see in a minute. So let me go back, and we can stop showing this and go back to our to the poll again. So let's see. Okay, can you see this again now? Okay, so commonly cited definitions of trust include primarily this one by Mayer that is cited quite a lot and has to do with the willingness of a party to be vulnerable to the actions of another party based on the expectation that the other will perform a particular action important to the truster.
And we don't see your slides.
Yeah, sorry, we're not seeing your slides.
Oh, well, thank you for letting me know. Go back to this again. How's that?
Perfect.
Yes.
Excellent. Okay, definitions. So the commonly cited definition that I just read most of has to do with taking risk. And Glickson and Woolley have summarized this: the tendency to take a meaningful risk while believing in a high chance of positive outcome. And trust is a heuristic that people use to simplify their lives. And it's a really essential component of any social interactions, actually. Other definitions, many definitions of trust focus on requirements, such as the types that we just saw in some of these definitions that we just showed. For requirements such as accuracy, reliability, and performance. And these have all been shown in experimental research to affect trust in the model. But morality information in other social contexts in particular has been shown to be more important than performance information. And in fact, your poll results suggested that you all agree with that the morality of what's going on, that the social benefits and the ecological sustainability of the AI is more important than these performance and accuracy requirements. It has also been shown that affect and trust, which both act as heuristics, and a heuristic is a mental shortcut or a rule of thumb that people use when they're thinking, influence one another, and they influence judgments and decisions in these kind of trust contexts, for example, in trust in an AI model. Extensive research on human judgment decision-making shows that we have two major modes of thinking, one which has been called system one, which is fast, and the other is system two, which is slow. System one is intuitive and emotional. It's our gut reactions, our affective responses, and the system two, which is deliberation or cognition, is effortful, analytical, and it's called slow thinking. And for those of you who have not read it yet, Danny Kahneman's 2011 book on thinking fast and slow provides a really good introduction to the science behind this. And the point here is that trust is a consequence on trustworthy, and how trustworthiness plays out is a consequence of both of these systems. So trustworthiness has been defined in the context of AI as the degree to which the AI warrants trust from the humans. Does it deserve to be trusted? So there are common terms that have been used here in trustworthy AI, and for explainability, we see interpretability and explainability. The definitions of the terms interpretability and explainability can vary across context and research domains, but they are very commonly highlighted in trustworthiness research and research on trust in AI. In fact, interpretability and explainability are often used interchangeably, and although interpretability is used more often in the machine learning community, some authors have made a clear distinction between the two. For example, explainability is said to refer to an active characteristic of the model, denoting an action taken by the model with the goal of explaining its internal functions for user comprehension. Interpretability, on the other hand, refers to a passive characteristic that makes sense for human observer. And illustrating this, Thompson and colleagues define interpretable as a property of the AI system that allows a human to understand the reasons for the system's output. And they define explanation as information provided by the AI system to the human that provides reasoning around why the system produces a specific output. And in our own group, we've talked about the fact that explainability is a sort of a post hoc characteristic, whereas interpretability is inherent in the model itself. So interpretability can also be divided further into two forms: results interpretability and model interpretability. And the former refers to information regarding what aspects of the data have led to the decision under consideration. The latter refers to the human ability to understand the model itself. So to sum up here, there are four types of factors that influence trust: user characteristics, and this can include people's expertise in mental models; accuracy, the more accurate and reliable and predictable the model, the more it is trusted; context, so trust is very much context dependent. And so, for example, in the weather context, it will matter what type of weather context you're in, and the explanations that are provided. So poor explanations, for example, low fidelity explanations that only highlight features of input data and don't provide information about what's influencing prediction, or for example, about the sustainability of the enterprise, can decrease trust in an AI model. And in the empirical world, self-reported trust measures can show a different picture than one would see when one observes trust as demonstrated by the participants' actions. So the guiding tenets of the research that we're conducting for trustworthy AI are that I just realized I'm not tracking this here. That AI and machine learning and other model guidance is a form of risk information. And so this is information that expert users and others utilize to assess and communicate about weather, climate, and coastal hazards. And we're looking specifically at weather forecasters to start with, but also emergency managers and other types of professionals who work with AI models. User engagement is essential to effective risk communication, and that means including developing effective risk information and XAI. And conducting convergent research is the goal. Integration of knowledge, data, and ideas through co-development, co-analysis, and co-interpretation, et cetera, is important to address compelling problems. You can see in this figure on the right by Lori Peek and her colleagues a framework for thinking about convergent research. And this illustrates how it's important to integrate through the model development and the research and co-producing with users what they want to see in a model and what is it going to help them understand whether the model is trustworthy or not. So in the context that we're in weather in particular and climate, there's been an exponential growth in the computational technology, and that's powered complexity, increasing complexity and increasing scales of modeling, both at micro scales and at global scales across the environmental sciences. This has happened in other sciences as well. And there's increasingly recognized need for convergent research, this type of research that integrates across disciplines and also across social and behavioral and computer sciences, increasingly powered by artificial intelligence. And AI and complex convergent science can be really hard to explain and to understand. And so for that reason, there's been a reference to what's called opaque algocracy, meaning that the algorithms just don't necessarily make sense to people intuitively. So expertise plays a really big role here, as you can guess. Experts have hierarchical, well-organized, and consistent mental models, and these are organized around the deep structure of the problem. They understand the function as well as the form of what's going on. And so think about this in the context of XAI. This means that experts in modeling and AI will understand what's going on with the AI. Other types of experts may not have this understanding. Understanding both the function and form requires deep experience And experts tend to problem solve by pattern matching because they understand what's going on and they're looking for a specific set of characteristics or problem. So they do this based on their superior recognition of problems. This is easiest to understand in the context of chess, where you can think about experts who can just look at a chessboard and know what's going on. Excuse me. So on the right here, you can see the Brotherton diagram. And the Brotherton diagram at this bottom of this slide begins to illustrate the complexity of Earth systems, but also the increasing complexity of environmental modeling. And it provides an example of how organized expert understanding of environmental systems can be. This diagram was developed by meteorologist Francis Brotherton. And it's very organized. You can see it's hierarchical, it's very structured. And it was seen at the time as all-encompassing for what was going on in Earth systems. But it also illustrates how expertise can result in a very narrow bracketing of problems, focused on a very specific set of problems and decisions. For example, human activities in this diagram are just in the very small right-hand corner of this diagram. But we know that human activities have influenced and influence increasingly many of the processes shown, including but not limited to terrestrial ecosystem functions, marine biochemistry, atmospheric chemistry, and albedo. So complexity is a challenge for explainability, especially for non-experts who lack the fluency. Excuse me. So you have to ask yourself as a modeler or as somebody who's trying to use AI models, what does it take for decision makers who do not have AI modeling expertise to be able to make informed decisions with these types of models and to trust them? So to sum up, experts pattern match in their domain of expertise. They look for these big patterns, but while lay decision makers who don't have the domain expertise use simplified mental models. And often they have to use many mental models to understand what's going on. The default decision-making strategy for non-experts is lexicographic, considering one factor at a time. So problem solving is as a form of search. It means that people are looking for solution, one aspect of at a time, and rather than pattern matching, which experts are doing. And this means that simpler explanations are far preferred. However, there are exceptions to this. One common reason for rejecting medical AI is a lack of trust due, for example, to the feeling that the AI is failing to take into account the uniqueness of the specific symptoms. Patients tend to think their own symptoms and diseases are more unique than those of others. And this is a form of complexity. So some forms of complexity are actually important in the context of trustworthiness. Explanation, and any explanation and understanding requires a simplifying assumptions, and understanding the limitations of those simplifying assumptions is really important, including the ethical implications of what's going on. Some authors have noted that explanations are typically highly biased toward expert users' understanding of the system, and this can alienate users who are less familiar with AI systems. Explanations that match the user's baseline understanding of the system tend to engender appropriate trust more effectively. So if you see an explanation that helps you understand the system in the way that you already previously understood the system, but more, well, it will increase your trust more than it would if it didn't match your understanding of the system to begin with. And Hoffman and others have concluded, for example, that explanations should be produced according to the user's needs, understanding, and goals. So this framework shown here by Wang et al. Can give us some insight into how to think about what's going on when we think about XAI in particular, and how people are going to trust, and what's going to what is the interaction between XAI and people's intuitive understanding or their decision-making patterns. So in order to decide on appropriate XAI system goals and user needs and underlying interpretability techniques, this framework can be helpful as it provides a guidance and maps different theories of human reasoning onto corresponding XAI techniques and strategies for designing XAI. More specifically, the red connectors shown here represent how such theories inform XAI features, while the gray connectors represent interrelationships between different human reasoning processes and between XAI features. For example, system one thinking that we just talked about, this sort of cognitive thinking, heuristics and biases, this gut and quick and fast thinking, can interfere with human hypothetical deductive reasoning, leading to confirmation bias. And here's and XAI can mitigate confirmation bias, for example, through saliency heat maps, showing people what they should be looking at or thinking about rather than what they might be thinking about intuitively. So in sum, in the research that's been done, we've seen a lot of different techniques that have been shown empirical results on how these things happen, what kinds of thinking people are doing, and how the XAI influences people's judgments of trustworthiness. Methods for conducting this kind of research or user testing to look at how explainability and interpretability of a model affects users' understanding include randomized studies where participants are randomized into conditions with and without AI assistance, user studies where participants are asked for their feedbacks on their experience, AI-assisted games, such as the explanation-assisted guess switch or XA game, where participants are assisted in guessing the correct answer with various levels of AI assistance. This research has also involved detection tasks where participants are performance in the task is evaluated with varying levels of assistance by machine learning models, and case studies that assess the use of interpretability tools by experts such as data science and clinicians. And then finally, there are expert reviews, which have been used frequently, especially with visual analytics tools, with the advantage of requiring very few expert participants who can identify a large portion of usability problems compared to lay participants in controlled experiments. So a wide variety of techniques. However, empirical research on trust is still relatively sparse and scattershot. The field is growing rapidly. The literature review reflects the inconsistent use of terms that we've talked about and overlaps between studies that examine trust, interpretability, and XAI. As we've noted, trust is social and affective. So it can include trust in the modelers, for example, and in organizations, as well as cognitive. So it can be a functional trust of the models and the guidance in their performance, for example. And there are very diverse social and behavioral science approaches to this field, but very little qualitative research that we've referenced or found so far. The studies illustrate the importance of context and the user characteristics for trust in AI. And we see that medical AI has received a lot more attention in the context of trustworthiness than environmental AI has. User characteristics are important, and studies of experts and professionals' trust in AI are still relatively rare, which suggests that it's an important domain for us to continue to pursue. And Mueller now has summarized very expertly several key XAI concepts that we'd like to highlight here. Explaining is a continuous process. Explanations guide further inquiry, enable the user to develop an appropriate trust in AI with continued experience. Explaining is co-adaptive. Both the learner and the user, as you've seen, participate, and the system participates in the explanation process. Explanation trigger, the violations of expectation trigger explanations. So XAI needs to understand what it is that triggers that are appropriate triggers of explanations. And explanations are also exploration. They help clarify what the boundary conditions are. And people are looking for when it is, what context the AI are in, is appropriate for. And finally, contrastive cases are really central to all explanations. Yes, so we have a few comments on the previous poll, and we are just about ready to dive into the next poll. And so let's see. Some people wondered if the poll was about AI models that currently exist or ideal. And I hope you're all looking at this. AI models interpretable.
Yeah, so I was going to jump in and say that we inadvertently also did a bit of a methods, give people some information about methods and about survey design and measurement error, because several people misinterpreted it. And so that is actually a really important thing. And it is one of the challenges that we have when we're conducting surveys and constructing questionnaires relative to other types of methods. So we wanted to be sure that we clarified here what the actual question was going to be asking about.
Excellent. Yes. And so, so we'd like you to, once again, so to clarify, and we'd like you to go to Slido again and try the next poll. So this poll is very much about an existing model and an existing XAI. So you'll see on the screen here, and is it large enough to read, Julie? Or should I go back to the previous slide? Okay, so this is a figure that is pulled from a paper by Emma Ebert-Uphoff and Hilburn. And we'd like you to answer these questions about this specific XAI.
Yeah, so go ahead and read the figure caption. We recognize that you're only getting a snippet of the explanation, but you could imagine that as a user that you might only get a portion of the explanation too. You wouldn't know as much as the developer does. So if you had this information, think about how you would interpret that and then respond to these survey items.
And Tasia, we're going to count on you again to give us a cue.
Yes, I will. Right now, there's only 6. They're coming in slowly. There's several questions.
Ah.
I'll keep you updated.
Yes, this is a little more complex because it requires to read the figure. And why don't I go ahead and read the figure text while you guys are answering in case anybody's having troubles reading it. So this figure shows the use of an attribution method, namely layer-wise relevance propagation, or LRP, to analyze a neural network model, so an AI model, that seeks to translate imagery from the geostationary operational environmental satellite into multi-radar, multi-sensor, or MRMS imagery. LRP results in the bottom row here show where in the input channels the neural network is focusing when predicting the multi-radar, multi-sensor value for a single central pixel. So using the LRP, layer-wise relevance propagation, indicated for various samples 3 strategies for the neural network to trigger large MRMS values, namely cloud boundaries, cold cloud tops, and presence of lightning in the geostationary lightning mapper channel. And you'll see here these channels, the geostationary lightning mapper input, the estimated radar image. So this is this multi-radar, multi-sensor imagery, and then the correct radar image on the bottom row. How are we doing on question? 100 votes. Okay, we're getting up there.
Yeah, 120 now, so they're going faster.
Okay, so we're how are we doing on time, Julie? Let's see. I think we're at time actually.
Actually, no, we're doing good. We have 10 more minutes in this whole session. We want to probably allow 5 minutes for some Q&A from Slido, but I think that gives us a few minutes to interpret the results from this.
Okay. So let's give it another minute or two, and then we'll take a look at the results. We've got some excellent questions from the previous poll, so we'll have to come back to some of these if we have time. 162. Okay, should we start looking at the results then, Julie? What do you think?
Yeah, let's do it.
Okay, so I guess I have to stop share to see what you're doing. Tasia, are we ready to start looking at the poll results?
Yeah, you should be able to see the first question now.
Okay. From the explanation, I understand how the neural network, this is just about split. It's hopping around here. So we've got about half. So this is a really interesting response. And it does make me wonder. I was wondering if we should have tried to do something more elaborate where we had to divide people into those who are more or less familiar with these types of models, because here's a case where your understanding is definitely going to be influenced by your previous exposure to this type of model. So we've got about half saying 44% saying disagreeing, 3% agreeing, 42% agreeing, so about split, and a little bit more strongly disagree than strongly agree. So not so easy to understand what's going on, clearly. Should we take a look at the next response? It's satisfying. Okay, so we do see, nevertheless, that about half, almost, so about half again, disagree or agree. And so let me say that I'm putting in my mind these mental confidence intervals around these results. So we've got 50% disagreeing and 6% strongly disagreeing, and about 41% agreeing and 3% strongly agreeing. So slightly more disagreeing than agreeing. But still, we've got about half and half thinking that this explanation about how the model works is satisfying. And any comments for anybody? I don't see any input on this in the polls yet. Okay, so next one, detail. So people want more detail. That's what I conclude from this poll result. 59% disagree and 9% strongly disagree that the explanation of how the model works has sufficient detail. So they would like a lot more, people would like more detail about what's going on. And probably, this is where the characteristics of a black box come in. You want to try to figure out what the AI model is doing, and the more information you can get about what exactly it's doing, the more satisfying it might be, right, too? So that people are feeling like it's lacking detail here. Next result. This explanation of the model shows me how accurate the model is. And so here we have still disagreement. We've got 52% disagreeing and 17% strongly disagreeing. So this is interesting because for me, when I look at those two images, at least I get the feeling that the explanation is trying to show me the accuracy, right? Because I've got this contrast between the actual radar image and the estimated radar image. But that's a visual comparison. And so it doesn't give you sort of an accuracy or a verification number of any sort, for example. So maybe that might be helpful. But there's some disagreement here about how accurate the model, there's disagreement that the model is showing the accuracy. Explanation is showing the accuracy of the model. And that could relate, according to the research that we've seen briefly presented, to people's dissatisfaction as well. Next question, please. The explanation of the model, of how the model works, seems complete. And here we have, we've got 59% disagreeing and 12% strongly disagreeing. So even more disagreement here.
It would be really interesting to think about for people to potentially put in Slido what additional kind of information they would want to actually have kind of the completeness of the explanation, given some of the consistent results that we're seeing. And I'll also note here that we only have about 4 minutes, and we do want to make sure we have people have the opportunity to have a good 5-minute break. So maybe, Anne, we can go through the last 3 items really quickly and then see if there's one question in Slido we want to raise.
Okay. Explanation of how the model works tells me how to use it. Okay, so here we have less disagreement, actually a little bit. No, actually we have more disagreement. 23% strongly disagree. So almost 3/4 disagree. Let's go ahead and go to the next so that was that was usability, and this is usefulness. Useful for forecasting. Here we have quite a bit of agreement, majority agreeing, though we've got about a third still disagreeing that the explanation of how the model works is useful for forecasting. And I think we've got, is that it? Let's see. Oh, here's the last one. So this explanation lets me judge when I should trust and not trust the model. And so here we have we have a split, but more strongly disagreeing than strongly agreeing. So we have a slight bias towards disagreeing that that the explanation helps you judge when you should trust or not trust the model. Okay, so I think we're ready to go back to that. Now let's see, sorry about this. I'm juggling 2 screens and a bunch of stuff.
Yeah, so I thought I would just pull out a couple of things. Actually, Randy, hold on, I'm trying to look at this on 2 screens too. Randy raises a really good point here when he says one example will never be sufficient to satisfy any scientist. This example could have been cherry picked. Either this example could have been cherry picked or absolutely, Randy. I mean, I think you're talking about how actually, this is going to come up in a couple of ways in the next couple of talks, but about looking at the value of a case study, seeing the results for one versus a set of performance or verification metrics over a set of cases, and the balance and the utility, I think, of both of those things. So that's a good point. Anne or Amy, is there anything else you wanted to raise? It's so hard to track all the Slido. Things are jumping around so much.
Let's see.
Sorry, Anne, I took back over the screen share so I could keep
sure
questions.
Oh yes, so the neutral point was so unsure answer. So yeah, so actually that's interesting because there was a neutral point in the scale originally. So so I'm not sure what happened to that.
But I think, Bill, you also raised just an interesting point here about how we collect this kind of data from users, and if we force them to agree or disagree or to take an opinion versus if we let them tell us that we're not sure. And that's an important aspect to the social science research and data collection that we do.
Yeah, and in fact, in survey methodology, there's been quite a bit of disagreement about this, about whether or not you should have a don't know or unsure option. I've worked with some survey methodologists who feel it is absolutely essential that you have to include an unsure point or a don't know point, because people's opinions are actually often in that space. The reason not to include that point is because there's some feeling that there's a latent attitude that people always have. They always have some sort of leaning towards agreeing or disagreement, and they're unsure is just their unwillingness to take the cognitive effort to try to clarify for themselves whether they agree or disagree. So anyway, we intended to include a neutral point, and I'm not sure what happened to it.
And there's so many other good things that are popping up in here, but I think we do need a break. Yes, go ahead, Amy.
Yes, I was just going to pop in and say, we deliberately built in brain breaks so that people could take a bio break, go grab your coffee, do whatever, come back in 5 minutes. But we want to make sure we're not taking your 5 minutes. So come back in 5 minutes and I'm going to give you a quick demo. Go snuggle your dog if you need to.
Yeah. And thank you all for being so game and participating in the polls.
We are going to restart in 1 minute. So welcome back from your short break. All right, it is 11 now, my time, Central. So we're gonna restart. Amanda can start sharing her screens. We're gonna jump into some actual case studies of using AI models with forecasters.
Cool. So I might give everyone maybe 1 more minute just to come back in before I really start getting into my talk, just because we were running a little bit later for the break.
Maybe while we're giving them 1 more minute, remind everybody, in case we have new people, because I can't see the participant list, about where to go get on the Slido.
I don't actually know where to go get on the Slido, so I can't, but someone else can.
Okay, I'll put it into the chat, and it looks like Anne wants to say something too briefly.
Yeah, I'd just like to say thank you all. I'm not sure what we can do about the questions, but we will see if we can put something in the online posting about them. We had some excellent questions. Also wanted to say that poll was based on questions and dimensions developed by Robert Hoffman and his colleagues. So we want to give him credit where credit is due.
Go ahead. I think you're ready, Amanda. And I didn't realize the Slido was on the live stream since we're on the Zoom version. So apparently you just scroll down on the webpage and you can see the Slido.
Okay, sounds good to me. All right, so hello everyone. My name is Amanda Burke. I am a PhD student at the University of Oklahoma, and I work under Dr. McGovern, who you were just heard talking. And today I'm really excited to talk to you guys about trust and hail prediction. And I have an interesting, unique perspective on this, just because when I was putting together this talk initially, I didn't realize how many years we've been looking through specifically hail prediction using AI and for operational forecasters, and how that's kind of changed through the years, which you shall see. And I didn't realize until, again, I looked at the summary of this. So just to give a little bit back, like some interesting information about what I'll be talking about the model, just so you have some information. Our input data, so what we're trying to do is emulate basically the Storm Prediction Center's probabilistic hail forecasting for day 1 outlook. So to do that, we used random forests, specifically with input data from the high resolution ensemble forecast system version 2. And for our target variable to do hail prediction, we use the MRMS, maximum estimated size of hail. And so this initial system was developed by David Gagne, who is now at NCAR, but this was for his PhD research. He was looking at a way to create gridded forecasts for hail, but not necessarily in the operational field, just for research. And so I took over in my master's using his work to then implement it with a ensemble forecast system that is specifically more operationally based, and to see how forecasters react to it during different experiments. And so we trained 8 different random forests, 1 for each one of the href-free2 ensemble members. And then for each random forest at a given grid point, we would average the prediction of, is there severe hail, is there not, across the ensemble. And so what this did is create probabilities that range from 0 to 100, because it's just based off of averages. And if we look here on the right, you can kind of see what the output looks like. So on the top is an example of the day 1 SPC probabilities for hail on, I believe this is May 8th, 2018. And on the bottom is our hail prediction from the method I just mentioned. And so what we can see is, here I just circled just 2 areas of interest. And so at the bottom, the dots are the severe hail reports for this day. And so really what you can see is for the SPC, the probabilities only go up to about 5%, but for our model, they went up to near 30%, which is quite different in magnitude. Spatially, they look pretty good, but magnitudes are off. And we see the same thing in the West as well. And so when we initially presented this work during the Hazardous Weather Testbed Spring Forecasting Experiment, which I will be referring to HWT, this is from 2018. And basically what the HWT is, for those who don't know, is multiple different researchers, academics, forecasters, et cetera, come together and evaluate different models, methods, things like that. And so for this, they were looking at specifically what we were interested in is our hail predictions and seeing how do forecasters, researchers, et cetera, like our hail predictions compared to an probabilistic guidance made by people at SPC and also the outlooks themselves, or at least an experimental outlook. And this is taken specifically from the website from the HWT. And what you can see here in the middle is our hail predictions. And on a subjective rating from 1 to 10, in the middle here, we have our machine learning from this year. And we weren't doing so hot as far as subjective ratings go with this specific model setup. We had on average about 4.5 out of 10 rating. And you could see it as well in the SPC and NSSL guidelines findings they put out, that our machine learning guidance was generally low in subjective ratings for the full period forecasts compared to the other guidance. And so this is what our initial setup was for transitioning an initially research-based model into operations. And so one thing that we did receive in feedback was that our probabilities were considered too hot or too high. And so to try and mitigate this, we changed our model setup, added a calibration step after averaging the graded probabilities. And so what this did is it mapped our values. So instead of a range of 0 to 100, they go from a range of about 0 to 60. So the different areas of interest don't necessarily change spatially, but their magnitudes now change. And this increased the forecast skill associated with our model. And more importantly, at least in my opinion, produced output that was much more realistic with forecasters' expectations. So if we look at the initial thing I showed in the second slide, I believe, in the West, our probabilities for, if we look on the very right, this is after calibration, they are much lower compared to the middle, which is our original model, and closer to the SPC guidance, which is on the far left. If we look in the middle of the country, same thing. Our magnitudes are much smaller, but spatially, the forecasts are pretty much the same. So for the 2019 Hazardous Weather Testbed, we submitted this model set up with the calibration, and we got much better evaluation metrics, where before we had on average about 4.5 out of 10 subjective evaluation from the participants. We now have about 6 on average, which is the box in the middle. And now, and this is interesting that I didn't even notice really until, like I said, I put this talk together. Now the feedback from this year was that the machine learning hail guidance scored higher than the other guidances, the HRF, TREF guidance. So we thought, okay, that's good. We're on a good track. How else can we, keep going more? And that is with the 2020 setup. And so what we noticed as well, in addition to the magnitudes being better, what we noticed with the random forest is sometimes they could be a bit off depending on the time of year that they were forecasting for, because our models were trained on hailstorms, and the highest frequency of hailstorms happen in May and in about the Central Plains. But this doesn't really help us if we're trying to forecast for like August or the Northern Plains and things like that. So for the 2020 setup, we added weighting. And I'll just go through the different example here really quickly. So on the very top, we have the SPC's gridded outlook for that day. Again, the black dots are the storm reports. The top right is the updraft helicity proxy. So specifically from the HRF v2, the high resolution ensemble forecast system version 2. And on the bottom are our machine learning forecasts. So the bottom right is the initial model setup that I was just talking about with calibration. That is what that would look like for this day. And we also added a new step, basically, that weights the examples input to a random forest based on their point in time or space, like a reference point. And so, like I said, we continue to calibrate our output to have the probabilities more in line with the forecasters. And what this weighting that I was just talking about does is basically, depending on the time of year, or if it's, again, in space, the examples that we input to the random forest that are closer to that either time specifically or spatial area will have higher weights and will be considered more important in the random forest than the points outside of that. And what that really did is it better captured the spatial temporal distribution of hail, which we saw not only in our forecasts, but when we were doing explainability and interpretation. So using permutation variable importance, we were able to see specifically in time, space can be a bit iffy, but in time, depending on when you weight your forecasts, the model that is specifically made for May versus a model that is weighted for August has different variables that it considers important for hail prediction that correspond well with the spatial temporal development of storms. So we input that to the 2020 HWT. And I will note that there was another machine learning model that was input or that was shown off during the HWT. Before this, I believe our group was the only machine learning for specifically at least hail prediction in the HWT. And so the red box is, again, the forecast that we were looking at. Average wise, our ratings didn't really increase with the weighting addition. However, we did receive some interesting feedback between the different machine learning type views, basically. And so looking at the right, the SPC was saying, you know, machine learning Burke tended to give sharper probabilities over smaller regions. What we heard in general from forecasters is it was really good at identifying the high hail threat, but the other machine learning product did have higher probabilities of detection compared to our product. And some other interesting feedback we got from that year is from one of the facilitators of the experiment that actually tweeted about our forecasting, about how AI could be a game changer, specifically for probabilistic forecasting and hail in this type format. And so that was the HWT 2020. This past year, we didn't really have any changes to our random forest model. It still had calibration and it still had the weighting schemes, specifically in time. We just added more data to train. However, this year we also added a deep learning type setup, which you can see in the middle here. And it's an example from May 15, 2021, taken from the HWT website. In the middle, we see the deep learning and the random forest models, specifically developed by me and my group. And you have different forecasts all around with the practically perfect or what a forecast could have been on the right, excuse me. And so while our probabilities are a bit low for this day, we see practically perfect was up to about 30%. In the middle, we see though, the deep learning actually had smaller areas of probability. It did miss a few reports, but it had smaller areas of probability, really highlighted where the different threats were going to be, where all the random forest method actually had more spread out probabilities, similar to the machine learning random forest Loken, which is on the bottom left. And then the top left, we see the href calibrated, which just had very low probabilities. And so it was interesting for me, and this was actually the first year that I did not participate, so I don't necessarily have a good indication firsthand of what forecasters were saying, and they also don't have the report out yet. But from what I've heard for the people that did participate from our group, is that a lot of people actually, a lot of the participants preferred the deep learning model over the random forest, even though the deep learning model is not nearly as tuned as much as the random forest is. This was the first year we showed it off versus the random forest model has been shown since 2017, I believe, or 2018. So it's just really interesting how the evolution of machine learning specifically during the HWT progressed. Especially this year, there were at least probably 3 or 4, maybe more, different models submitted of machine learning for different types of prediction, not just from the group that I'm in, but in multiple different groups. And it seems to be as years go on, there's a lot more trust in the models, but I believe that also has to do with more exposure and just different types of knowing how the machine learning models are working. So with that, I'm fully welcome to take questions. Our discussion would be great because, like I said, a lot of this has to do with not only the reports that the SPC gave out, but also my personal experience, not only submitting these models, but being a participant in the experiments and hearing kind of what people were saying.
You have a bunch of questions that are showing up in the Slido. Ah, good.
Okay.
And she just switched to Slido, so you should be able to see them.
Okay. Here, let's see. Make this full screen so I can see. Yes, so how are they graded? So that's an interesting question, and it does change between years. I don't know for sure exactly how the different subjective ratings went into the report. Typically, what I understand as a participant is they are the average ratings of how well, like, do you think this forecasted for this event across the participants? But that would be something definitely to look at in the actual reports themselves, because I don't know. Is the weighting a heuristic? Not entirely sure what you mean by that. I don't know.
I'm going to guess that some people, because there were 2 questions about the weighting, that some people were missing the explanation of how the weights were done.
I can go into that if people are wanting me to. That's kind of something separate.
Do it. But I'd say just do it briefly, because you have another one down there. Explain the weighting for parameter, etc.
So what the weighting does is it uses an exponential decay function to specifically within the random forests. When you are doing the scikit-learn package, you can weight each input example into the random forest. So the different predictors that you have and the different rows of data you have, you can apply a weight that basically changes up, I believe it's the Gini index or whatever index you use for random forest specifically, to basically say, hey, this data point with a higher weight compared to a different weight of data point is going to be more likely chosen as an important variable in the random forest setup, so higher up in the tree than a different data point. And so what that does is with the exponential decay function, especially in time, is that the data points, say in May, I did this by month, you can do it with this method however time period you want. You can do it for a day, you can do it for a week's length, whatever. But outside of the time period that you care about, the weights exponentially decay, in that case in time. So like 2 weeks after the end of May or the beginning of May, say, the data says, hey, these are no longer autocorrelated, these are not more important. So let's just decrease the weight. So we're still getting, you're still inputting the data, you're still getting the general information about hail formation, but specific to the time period you care about. And so what that did is, especially like I said, for May versus August, if we don't have a lot of hailstorms specifically in August, we still get the general information about how hail is predicted and how it forms, but more specific to the types of environments that occur in August. And this makes it also easy because we didn't have to do anything different with our input data, just add that weighting parameter. So we didn't have to rerun anything for, we do object-based prediction for this. We didn't have to rerun any of the objects or anything like that, just add an extra parameter when we're training. And it doesn't add time to training either. Okay, I knew this was gonna be a question, why the deep learning performed better. I think because it has to do with the different spatial information you can get with deep learning versus random forests. You lose all of that when you're using random forests, even though we were doing an object-based format. And I think not only that, but just even though the random forest was tuned more, I think maybe that was at a detriment just because you never know really what's going to happen for a given year. I believe this past year had a decent amount of hail days, but the other previous years just didn't. And I think that definitely helped too. So parameters. So for the random forest, we had about 28 input parameters from the href, including geopotential height at different levels, temperature, dew point, different storm objects, so updraft helicity, updraft, a few other things. And so I see you have a reference point in the calibration with SBC reports. I'm not entirely sure what you mean by that. I'm sorry, I don't really know what the second part of your question looks like or what that means, sorry. How do we define the severe probability for hail? So for the random forests, that is based off of, so the random forest, they first classify an object for, is it going to be severe hail or not, based off of the MRMS mesh values. So if the mesh values associated with that object are greater than the severe hail threshold, they will be considered severe, or at least that's how we train the model. And then there's another random forest regression that then predicts hail size. And from there, converting that to binary probabilities, is it greater than the threshold of severe hail or severe hail or not?
And Amanda, I'm wondering if maybe not everybody knows, since we have a lot of international people, that threshold for severe is 1 inch.
Yeah,
Yep, you might just want to follow up on that.
Yeah, so the severe hail threshold is 25 millimeters. The SIG severe or significant severe threshold is 50 millimeters. And then in inches, that's 1 inch versus 2 inches. For one, I believe personally for this question that is highlighted that a random forest, it doesn't even have to be for 1 month, but maybe for 1 season would work a lot better than one, as they say, mega random forest for all times of the year, just because, excuse me, when we tried to do that just for spring, summer season with a model that was trained on everything, it really did well in May, and it did not do so well when it was outside of May, just because that's with the highest frequency of reports. So I think tailoring each random forest would be the best option if you really wanted to get good accuracy. Excuse me, I'm gonna sneeze. I have 3 more minutes. Yes. Okay. And so, overfitting, we did different regularization things. Beyond that, I think overfitting, especially with like magnitudes, that's part of the calibration step. But other than that, just trying a lot of, having a lot of different data set for our training data. We have back to 2017 definitely helped with overfitting, just we had a lot of different examples. So I'm sure that, so for the random forest versus deep learning methods, I don't know for sure an example off the top of my head where they didn't perform very well. I'm sure they are there. And I think it's definitely something that we really should look into and what went wrong. For the most part, from what I could tell, it was typically the data that was coming in. So if they're in the object-based format, you have to have a certain variable there or the data there in the ensemble to create a storm object to then predict something. With the deep learning, it wasn't object-based, it was more grid-based, but still if the model wasn't necessarily keying in on the right area for the data, we might not have had as great of a forecast. So it really is ensemble and data dependent in that case. That could cause issues for a certain case or two or more. I think I have 1 minute left. So how to interpret random forest with domain knowledge, what makes it trustworthy? I think that's a really good question. From what I have experienced and just giving talks, especially to forecasters and to people at the HWT, what really helped with trust is explaining exactly how the input data is processed, not necessarily what exactly is going on in the random forest, but what input data is input, how it's pre-processed, how it comes out and really what has the model learned. And so that's where I kind of briefly touched on the variable importance. Showing that and showing what the model thinks is important really helped in trust. Because if I can show forecasters or other people, hey, this model is really keying in on this variable and this makes sense in this context of specifically hail prediction, that definitely helped with trustworthiness, because the model is learning things that we understand. Granted, this could also be a detriment if the model is learning things that are correct, but we don't understand. So it's a give and take.
Well, that maybe is a nice, perfect segue to the next talk. Yes, go ahead, Amy. Was there something you wanted to say?
I was about to say that you were next. I was segueing. You said it.
Yes, that question is great. It connects back to what Anne talked about before. Then Amanda gave this great example of one effort to develop explainable AI for hail probabilities. And let's see if I can share my screen now. Of course, when you do it, let's try this. Does everybody see that okay?
Yes, looks good.
Okay, great. I'll put it in presenter mode here. So like I said, I actually think that that question was just like a perfect bridge among all the things that we're talking about today. So just the second part of what Anne and I wanted to cover today is really now digging more into thinking about how do we examine trust for users, and just to kind of, again, connect all the dots. So Anne definitely covered a lot about the literature, including conceptually, how do we think about concepts of trust, trustworthiness, explainability, and interpretability? What are those features of trustworthiness? What are some of the ways that even empirically, as she mentioned, Hoffman and Mueller and colleagues have helped us think about ways that we can measure explainability. So she really covered that literature. Amanda just gave a great example of one effort to develop explainable AIs, again, specifically for hail probabilities. And there's going to be some follow-on talks that will also show some other examples. And even though Amanda talked a little bit about collecting some data from the hazardous weather testbed, we really want to augment that and think about what are some other ways that we can do empirical research with expert users. And really, if we take this Venn diagram, kind of the nexus of those three things, it really constitutes the risk communication research that Anne and I are co-leading as part of the AI Institute. And we look at this through the lens of risk and risk communication, because of course, when we're thinking about weather and climate and coastal hazards, those are all a type of risk, right? They all have the potential to cause harm if these events occur, and depending on how bad, how intense, or what the magnitude of those are. And then, as Anne already talked about, we really do think about AI and machine learning guidance as a form of risk information. So it provides information that different expert users, usually users who are more upstream in the whole forecast and warning process, that they can use to assess the threat, but then also communicate it to different users downstream, potentially with the goal of mitigating risk. But what's really important is that when we think about developing this information, whether it's risk information more generally about the hazard, or if we're thinking about AI machine learning information, we have to think about how it gets developed and will be used in this broader context of these expert users' decision spaces. So thinking about their goals, their barriers, their values, their experiences, what other information they have, because often we're dealing with a very information-rich environment. And in order to do this kind of work, to consider that context, this is sort of a tenet of risk communication, as Anne talked about, this kind of iterative engagement, two-way and often ongoing, so that we can develop the information is really quite critical. And so just to kind of give you a sense of what we're doing with the Institute, Amy talked about the Institute and what our vision is. Again, the goal is to create trustworthy AI so that we can better understand and predict high impact weather, but with the idea that the information will be trusted and used by these different expert users. And so what Anne and I are doing as part of the risk communication research that we're doing in conjunction with the rest of the Institute really is oriented around these goals. We want to better understand all these topics that Anne talked about, these key aspects of transparency, explainability, reproducibility, representing uncertainty, and so much more, and how they influence trust for different environmental science hazards. We want to think about developing models to estimate how people's attitudes and perceptions of AI trustworthiness influence then how they perceive a risk, and then how they might use that information as they're managing their environmental science hazard context. And then of course, develop methods so that we can inform the development of trustworthy AI approaches and how it should be provided so that we can improve this decision making. So these are our goals. And then just to give you a little bit more context, these are some example research questions and hypotheses that we've framed to really guide some of the empirical research with users. So we've got this very broad, and these are just a subset of all the research questions and hypotheses that we have, but we can start with this kind of broad set of research questions. How do expert users, and in particular today I want to focus on weather service forecasters because that links to what Amanda talked about with David Wilby and also some of Randy and Ryan's work. So how do those expert users think about concepts of trustworthiness, interpretability, and explainability? To what extent do how they think about it actually match how AI developers think about it? I mean, this is part of what we're all here at the summer school grappling with. Where are there key mismatches that could really inhibit the use of AI-derived information? Are there ways that those different expert users think about trustworthiness that are not on AI developers' radar, so to speak, but that should be? So this is kind of really guiding a lot of what we're doing. And then from there, and based on some work that I've done and many other people in the weather community have done, and building on work by Hoffman and Mueller and so many others, we can frame a number of different hypotheses. So some of these hypotheses might be that forecasters might be more inclined to use the guidance that resembles something that they're familiar with. And Amanda's work, where she was showing her development of the hail probabilities and developed in ways that match some of the SPC probabilities, is an example of this that we can empirically test. We might hypothesize that forecasters will want more nuanced verification of the guidance beyond just the traditional bulk verification metrics. And this was something that Randy already brought up in the previous talk, but David's work is going to empirically start to show some evidence around this. Or we might hypothesize that forecasters will have greater trust in guidance if it emulates known meteorological processes and features. And this is also something that Ryan and Randy's work will provide an example that we could empirically test these kinds of things. So these are, again, are just some example RQs and hypotheses. But what I wanted to then next dive into, we talked about showing a model. And ideally, I think originally we wanted to really focus on this in the context of hail, but we're going to pan out a little bit more. Because I mentioned that when we think about developing guidance or developing any kind of risk information, we really have to understand those different users' decision contexts. And so if we're thinking about weather service forecasters, it becomes important to think about kind of what is their job, what is their workflow, what kind of information do they currently already have, what are they doing, what are their goals, all of that. And so I wanted to present kind of a simplified working model of a forecaster's workflow so that then we can think about all the different places or some of the different places where trust is relevant and how it's located and how it emerges. So we can start here when we think about a National Weather Service forecaster, or forecasters probably even internationally. When they come in, there's a shift change, there's a forecast briefing. They're maybe thinking about what is the current status of products that are already in effect. What are some potential products that they might need to issue depending on the risk or the hazard that might actually manifest. There's more of an effort with forecasters to really connect and think about providing information to their core partners like emergency managers, DOT, schools, all the people who might do something with a severe product. So what are those interactions like? What kinds of considerations and so on. So that's kind of the first step. And then forecasters often talk about doing the forecast funnel. So they might be analyzing data initially kind of on a broader spatial or a synoptic scale. And there's a lot that goes into this. I've just tried to capture some of this here, but they might do a hand analysis to see to get a picture of what the atmosphere looks like right now or maybe 15 minutes ago so that they better understand what they're dealing with. They have all sorts of numerical weather prediction information available to them, global and regional guidance, including deterministic, so guidance that just has one realization of the atmosphere, but then ensemble guidance, which gives them an envelope of possible realizations of what the atmosphere might look like in the future. They have a lot of observational data, satellite data, radar data. They're considering model skills and biases. They're looking for the strength and placement of key features and key ingredients that contribute or are set up for the kinds of hazards that they're forecasting for. I've listed some examples there. They talk a lot about maybe comparing a model that is valid at a current time or a recent past and comparing it against observations so that they can see how the model are handling things. Has the model caught up? How well is it doing? They look at different aspects coming out of an ensemble. They might look across all the different model guidance they have to see how much consistency or inconsistency there is among all the models or even the ensembles. Or of course, they're going to look at stepping the model output forward into the future to sort of see how it's representing the atmosphere and how it's going to progress. So they do this at the synoptic scale, and then they narrow in and think about these kinds of things, really similar kinds of things at finer scales, at the mesoscale. And here they might be looking more at the regional or the convection allowing guidance, again, both deterministic and ensemble, still looking at all those obs, considering the model skills and biases, thinking about, again, kind of key convective ingredients and contributions to those particular convective hazards, still looking at the models and how it compares against obs, looking across models, stepping it forward in time and so forth. And I sort of have represented this as a one-pass linear process, but of course it's very iterative, and forecasters will tack among the broader scale and the finer scale as necessary. And then they make these decisions. Do they consult with others, either in their office or in other offices? Do they issue the product? Maybe they don't need to issue the product because it's not needed. Maybe they wait for additional information, and that could be new model runs to come in or new observations to see what the atmosphere is doing. And of course, this whole decision context is shaped by key contextual factors of what is their forecast role? What is their purpose that day? How much experience or expertise do they have? Are they dealing with time pressures to get something out? What season is it? What sort of potential impacts might there be if, say, like there's a large event going on in some areas? And then I've also listed down here in the lower right-hand corner some kinds of questions that might be driving their analysis that they're thinking about. You know, will all the ingredients come together? Will they be of sufficient magnitude? What could blow the forecast? That's a key thing. You know, what's the mode? Will the hazards be severe? Amanda was just talking about that, or sub-severe, because that shifts what they're looking at and what products they issued and so forth. So we'd love to be able to show some data. So kind of, you know, in contrast to the survey questions that we had earlier, we were talking about the value of maybe qualitative data, and we're planning to collect some data specifically focused on AI and machine learning. But in the absence of having that for today, we have data that we've collected from other projects with weather service forecasters that, even though it's not specifically focused on some machine learning guidance, it still gives us a sense of what they're looking at and where and how trust is located and how it's really relevant, so that we can think again about developing machine learning guidance that sort of fits into this broader picture. And so I'm just going to show a couple of examples of this to sort of set up what David's going to be talking about next. But on these next few slides, got the quote in one area, and then I've sort of highlighted the part of that workflow or that forecaster model that this really speaks to. So what we see here with this interview quote with this forecaster, this person is saying, you know, we do look at surface temperatures, dew point, pooling, moisture. We look at derived fields like CAPE and SIN that come from the high-res model solutions, and mainly do this to see, does it look like it's matching reality, at least from an initial state of the atmosphere, whether it's where the boundaries are or the fronts. Does the model have it in the right place? Does the dew point match up relatively well? So in this case, this person is really saying, they're comparing that model that is valid right now or in the recent past against those observations. So even though they might trust the models generally, or even trust a given model, they still want to evaluate how that model is doing for that day, for that given scenario, to know how much to trust it. There's a lot on this slide, but I like it because it's so rich and it really does show the information-rich environment that the forecasters currently have. So let me step through this here, where this forecaster, who's an SPC forecaster, a Storm Prediction Center forecaster, is talking about how I really do like this one model, the RAP model. If we get this ingredient, MLK, mixed layer CAPE, at a certain amount, 1,500 joules per kilogram, with 50, 60, 70 knots of effective shear, well then, yes, you're gonna have problems with the convection. But my concern, and he looks at this other model, is the NAM model's in here. Here's CAPE. It's got somewhere around 500 to 1,000 maybe, so less than what the RAP model is showing. I'm just not sure we're going to get 1,500. If I thought we were, then I would say we need to go enhanced risks. So that's one of the outlook products that SPC issues. And it's kind of, when you go enhanced, it's a really big deal. But this person says 2 main things are holding me back. Then looks at another model, the Euro, and says this widespread convection. And it's not just the Euro. You can look at the GFS, and got a lot of convection down here. And then this person draws on their experience by saying it's not a common occurrence. You get low-level jet strengthening throughout the day, and then can get low-level warm advection, precipitation advecting into the area, and then this area gets hosed, and it just doesn't destabilize as much. So again, kind of going back to this open question of instability. So what we see here is this person's evaluating trust by comparing different guidance, and then also over time, and looking to see if there are different kind of key important signals that really can reduce the confidence in what's really going to happen. And then of course that shapes whether or not they issue a certain product. And then just one more example, actually 2 more quotes here just to kind of drive home some of the points. Another interview here with a weather service forecaster at a local office who will talk about how sometimes the guidance can look so real world that it's very enticing, but it can also be really wrong. And they have to mentally guard against that because it's so convincing, it's so detailed, but there are many times that the real atmosphere has other things to say. So really touching on this idea, and I think this has come up even more, and this is something we're talking about in AI4ES regarding some of the machine learning guidance, that the guidance can be really precise, but that doesn't necessarily mean that it's accurate. And so that shapes their trust in being able to use it. Or you have a forecaster here who will say that we do have some tools on the HREF, which is an ensemble, but the last mile still isn't there because you'll get big probabilities that are coming for tornadoes along a cold front because the updraft helicity is high and the environment looks really good. But the problem is your mode is wrong, and we can look at the other high-res guidance and really know that. So they're considering the model skills and biases. They're really looking across models at a given time to look at that inconsistency, and also bringing, of course, their expertise and their knowledge about the environment and what's supportive of some of these kinds of hazards when they're considering how they're interpreting the different guidance they get. So again, thinking about their current situation, but also how these types of ways that forecasters think about trust and analyze different kinds of guidance might apply in the context of machine learning information. So just to summarize here, I think all of this stuff that Ann and I have been talking about and connect to David and Randy and Ryan, we really do see, of course, that trust and trustworthiness are very multifaceted. I think we're starting to get a sense from the literature and from empirical work about all the different dimensions that matter, but some of the things that came up in Slido earlier were other ideas that people had. And I think that there's opportunity for new things to emerge that are really important to why people trust things and how they trust and use the information. And then we have a lot of the ideas from the European guidelines, from the Mueller and Hoffman, from so much other literature about what are some of the features that we need to keep in mind when we're thinking about developing explainable or interpretable AI so that we can promote more trust and trustworthiness in information. But empirical evaluation with users is always essential to know what works, when, why, what doesn't, how does context play in, because it really does matter, especially when we're thinking about some of these professional or expert users. And then also, again, what's missing and how can we identify by working with these users things that are missing so that we can use that to guide future development. So I don't know how I am on time. I'm gonna stop sharing so I can maybe go back here to the Slido, and then hopefully we'll segue nicely to David's.
Yeah, so we have a few questions here that are coming up. Julie, can you see them now?
Let's see here.
So first question here is, what is the take of the WMO on the use of AI for forecasting?
Great question. I don't know that I know the answer to it. I don't know if Anne or Amy knows. Let me think for a second.
I don't know if the WMO, I was thinking in my reply, I almost replied in chat that the ECMWF has a nice statement out about AI, but I don't know of one for the WMO.
So part of the thing, I think, I don't know if I have a really clean answer to that, but the WMO has, they call it high impact weather effort. And I believe that they are doing some AI as part of that. And I'm on like their communication task team, and the role of AI has come up there. I'm trying to think that's probably more because I brought it up. So I think it's something that they're interested in exploring, but beyond that, I don't know if they have kind of a set of guidelines or principles, which I think ECMWF maybe has a little bit more codified. Is that right, Amy?
Yes, the ECMWF has a 10-year roadmap, and they had for the use of AI, and it is an excellent document. I highly recommend it.
Great question.
Thank you. Can you see this next question? I've seen forecasters at work in India, where they give more weightage to synoptic conditions followed by satellite image data, and then finally numerical weather prediction. They still call NWP numerical guidance. So can AI ML techniques supplement this in operational scenarios to establish trust?
Yeah, I think that's a great question. I mean, I think it's an empirical question. I think that so much of what the goal of AI4ES and what other people are doing is really with the idea that it will supplement. And I guess maybe what's embedded in this question is the idea of supplementing maybe more at the mesoscale. But I also think that there's possibility to supplement it at the synoptic scales. I think even Amanda's work starts to represent that a little bit. But I think the other thing that you're picking up on here is that, so I think lead time really matters. And that's one thing we've been thinking about quite a bit, because I definitely have experiences where forecasters will tell me when things are kind of unfolding in the moment, they are going to rely more heavily on the observations because that's what's really happening. And they have this idea that they can just sort of linearly extrapolate into the future. I also think one other aspect, and part of this depends on the different roles of the different agencies, is you'll have different people in a forecast office who might be looking at different guidance for different reasons. And so having a role of a meso-analyst, which they have increasingly in some of these areas, that can be looking at some of the shorter term, but still AI guidance, I think can really kind of fit nicely in there. How are we doing on time? Is this where I'm trying to...
Okay, you're doing great. We're in the Q&A period.
For some reason, I had in my mind that this is the time to go to David, so we're good.
Yeah.
Is there agreement in the meteorology community on what is? Oh, great question. I'm going to let Amy take this. On what is AI or machine learning? I will say that we've had conversations among ourselves in TAI4ES about this exact thing, which is part of the reason I felt like I was justified showing some of the quotes from the forecasters about how they're looking at NWP, because some of that might be AI. But Amy, you're more expert in this.
That is an excellent question, right? Because I think everybody agrees that deep learning and random forests are machine learning. But, we've had a lot of discussion inside AMS, even outside the Institute, just, what is regression? Regression is really machine learning, but it's also a statistical method that's been around for forever, right? And it's model output statistics. And people didn't call it AI and machine learning. So I think the line at some point can be slightly fuzzy. And also, if the question's asking what the difference between AI and machine learning are, which is also another discussion we've had. If I draw a Venn diagram, machine learning is inside AI, AI is the superset. But the general press level, like when people just talk, they just say AI. So the difference is that machine learning is adaptive. AI is just about the intelligent methods. It can involve search as well. I'm teaching this. I teach it at the university level. I think for the purposes of using it inside the meteorology community, we've just stuck with the AI word because that's what's showing up in the popular press, and it is the superset. Oh, and I didn't answer the last question. Do any of the products on your slides, RAM, RAP, NAM, GFS, use AI/ML already? So far as I'm aware of, the only AI that's in the operational use of any of those models is in the MOS. But there's a lot of operational stuff, or a lot of stuff that's not quite operational being tested, like what Amanda talked about.
Yep. I think Amy's right there. And I think one kind of maybe messy area, Amy, and you can speak to this better than I can, is some of the like post-processing of information that's coming out of the ensembles, whether it's operational or experimental. Some of that might be machine learning too, although maybe it's at least more accurately characterized as AI.
Yes, I would agree with all of that. The post-processing, a lot of it has statistics and AI. Yeah. That next one, by the way, that's a perfect one to drive us into the XAI. So I love that one. And also to say that we're going to talk about biases on Wednesday. That's the entire day of Wednesday. We're going to talk about ethics and biases. But I think that one will lead us right into the XAI. But do you want to tackle some of the others?
Yeah. How do we weight data-driven insights versus model predictions versus expert intuition? I think Amy's right. I think that this is a great question. I don't know if I have a great answer to this.
Yeah, I feel like putting that one into the XAI because that's what they're going to talk about.
Great. Thanks for the presentation. How do you validate your models, the accuracy of your models in terms of metrics used? You can come back. We'll be okay. Why these metrics for validation? So I'm not sure I know what model you're referring to, Simon. If you mean like the forecaster workflow model, that is just a working representation conceptual model that's really based on a lot of work that several people have done.
I think he's talking about the Hale model, maybe. Is that?
That's what I was wondering, if we're kind of casting back to maybe Amanda's work. Do we want to give Amanda a chance to quickly jump in and talk about validating the models, the accuracy of your models? I mean, Amanda, you have some verification statistics from your work, right?
Whoops, she's on silent. We can say that in our own work, we're planning on doing eventually more rigorous and not more rigorous, but different experimental work and also longitudinal survey work. So we'll be looking at a variety of ways of validating what we learned when we go in and look at forecaster workflow and trust.
Yeah, just to amplify what Anne just said, I think that part of how we designed TAI4ES was really multi-method, with the idea that we are triangulating, and we really do think about what is valid and generalizable by doing kind of the initial qualitative work that is much more exploratory, and maybe a little bit of exploratory work with the experiments, but then we will kind of get into more of the summative by putting some of this guidance in front of forecasters and different users. We're not just focusing on forecasters, so I should say that, and having them use it kind of in quasi real time and then providing feedback. So there's multiple ways that we're validating what we're learning.
Amanda, did you want to try to
Sorry.
tackle?
Dog barking, so I didn't want anyone to necessarily have to deal with that. Just really quickly, because I don't want to encroach on time. Typically, at least if you're talking about the hail models, we validate them based on reliability is a big one. That's typically what forecasters want to see, is how reliable is the forecast with respect to either the local storm reports or the specific actual hail size values. And beyond that, we do skill scores, sometimes the Breyer skill score. And then another really key thing to look at is the subjective kind of a verification. How well do the magnitudes line up? How well do they show spatially? Because I believe that's really important beyond just numbers and output. What does it look like? Is it useful?
Great.
Thanks, Amanda. Other forecasters seem to be willing to trust AI enough to verify its trustworthiness. How is this trust fostered? Well, so I think, first of all, there's an empirical question about whether or not they are willing enough, willing to trust AI enough. But I think that this question of where trust comes from is kind of part of what we're all really trying to assess. So in some cases, like Anne touched on this, it's relational. It's knowing the people. We have a whole set of questions that we're going to be asking as part of our interviews, but it's knowing who developed that information. Performance is one key aspect of how trust gets fostered, but even knowing some of the sort of subdimensions of that, how performance is important to people. Again, this goes back to seeing bulk statistics, seeing them segmented in certain ways, like by season or by storm mode, seeing case studies. Again, this will point to something that David will be talking about. We've really seen with working with forecasters that this explanation as exploration that Anne talked about is really important, so that they can actually interact with information and maybe begin to tease apart, knowing kind of what went into the guidance, but also seeing how the algorithm or the guidance gives you certain realizations for this scenario, or stepping forward in the future, or looking at it across, like for archive cases, is really important. What else am I missing, Anne? I think I'm touching on a lot of these.
Yeah, let me, Tasia, can I borrow the screen for a second? And let's see if I can do this. And just share this briefly as we go forward. Just to go back, the literature suggests that these are the reasons people trust AI. So this would be all of the things that Julie just touched on now, and some more. So a model would be trustworthy if people understand what it's doing. If as Julie mentioned, the performance, so accuracy, reliability, reproducibility, that the data have been developed, that the model has been developed on fair data, that the model has been tested extensively. And so all these things that Amanda talked about too, these are all really important in trustworthiness. And we can see that there are a couple of other aspects here on the XAI side that many of you called out in your responses and the questions. The lack of detail. Detail seems to be important to people. Accuracy is important to people, whether it's usable or useful. So those show up both in the quotes that Julie showed, but also in your comments and in your reactions to what you saw. So I will stop sharing again, then we can go back to the questions.
And I think one thing I wanted to say, because this really goes back to one of the comments when we were showing that example of Emma's and Kyle Hilburn's, and we just kind of gave the quick figure caption. We were trying to use this just for illustrative purposes to have people look at some aspects of the explanation and rate on these features. But I think there are questions of, what's the right amount of explanation? How much is too much? And how can you do this when there's so many different pieces of information? And how does this vary across users? And so I think these are additional things that we'll be investigating as part of this effort. These are great questions. All right, maybe one more minute. Anne, were you going to say something?
Should we take one more question? Let's see.
AI is so accurate enough for forecasters to rely on. Well, I think this segues nicely to what David is going to talk about, and maybe what Randy and Ryan. I think, you know, the verification or the performance of it is a key piece, and there's different ways of doing that. And in some cases, I think the forecasters themselves would say it's not accurate enough. They know when it's wrong, and when they're no longer going to use it. I think accuracy is an important aspect, that a really kind of complex idea, because sometimes forecasters will say, well, I know it's got this in the wrong place, but it's still really useful to me. So this is, I think, a very complex, multifaceted question.
Yeah, and we have this top question here is, are there ever situations where experts have intuitions that aren't supported by data? And I guess we'd say we have to look at the evidence, but the evidence that we've seen so far in the literature suggests that this does happen. So.
Great. So I think, oh no, we have a break, and then we segue to David. But this way everybody gets their 5-minute bio break, and then David's going to have some really interesting additional empirical results to show. So everybody come back at the top of the hour, and he will take over.
So that's what I was going to say. This is your chance to wiggle, grab your coffee, run around, stretch your brain, do something active so that you have 1 more hour that you can be interactive and asking all these fabulous questions. And we'll leave the questions up a bit longer this time. We've been trying to clear it so that it's, you know, the next person's questions, but there are some good things in there, and try to leave them up for about 5 or 10 minutes of the next talk so that Julie and Ann and others can interact in the Slido. See you in 5 minutes.
All right, are my slides showing up all right?
Yes.
Cool.
And it is the top of the hour, so feel free to start, or feel free to give yourself 30 seconds.
All right, I've actually got a lot of material to get through, so I'll go ahead and get started. Hello, everyone. My name is David Harrison. I am a research associate at the University of Oklahoma's Cooperative Institute for Mesoscale Meteorological Studies and the National Weather Service's Storm Prediction Center. I specialize in developing probabilistic forecast guidance to predict high impact weather events. And my position at the Storm Prediction Center allows me to often be involved in the transition from research to operations. So machine learning, deep learning, and other artificial intelligence methods have become popular tools in the meteorological research community. And indeed, there is a large amount of research, both in the literature and in practice, that suggests artificial intelligence could be valuable in an operational setting. However, artificial intelligence techniques have yet to be widely utilized within the operational community. Now, there are multiple studies and collaborations, some of which you've already heard today, that are ongoing to investigate different human and technological factors that can influence whether and how artificial intelligence methods could be integrated into the operational workflow. My presentation today is going to specifically focus on the questions of how does the operational community perceive artificial intelligence-driven products? What are the challenges to implementing these artificial intelligence products into an operational environment? And how can we, as developers and researchers, better tailor artificial intelligence research for the operational community? Now, to help answer some of these questions, I developed a survey and presented it to participants at the 2021 Hazardous Weather Testbed Spring Forecasting Experiment. Amanda mentioned earlier, the NOAA Hazardous Weather Testbed Spring Forecasting Experiment is an annual experiment hosted by NOAA's Storm Prediction Center and the National Severe Storms Laboratory, and invites participants to investigate a variety of numerical weather prediction models, convection allowing models, machine learning models, as well as derived output for the prediction of hazardous convective weather. Now, normally the experiment is held in person in Norman, Oklahoma, but due to the ongoing pandemic, we were forced to be fully virtual this year, and so we conducted the experiment over Google Meet. This did allow us to invite over 130 participants across 5 weeks, including individuals from local National Weather Service forecast offices, the National Weather Service Environmental Modeling Center, various oceanic and atmospheric research laboratories, cooperative institutes, NCAR, individuals from academia, as well as international research and forecasting agencies. Now, the survey itself was presented to Spring Forecasting Experiment participants every Monday immediately following the experiment introductions. Participants were told that the survey was voluntary and that their responses would be kept anonymous. The survey was composed of 10 questions, including 1 multiple choice question, 5 matrix table questions, and 4 open response questions. And you can see an example of the layout of the survey for the first couple of questions in the screenshot on the right there. We were very excited to receive about a 70% response rate from the experiment participants. This included 92 completed responses from 36 operational forecasters, 38 researchers, 16 academic faculty or staff, 10 students, and 7 individuals who identified themselves as other. Now, the keen eye will note that those numbers do not add up to 92, and that is because some participants classified themselves in multiple categories. So, for example, some individuals identified themselves as both a forecaster and a researcher. One of the questions that we asked was for them to describe or estimate their knowledge and understanding of machine learning techniques. And you can see in the plot on the right here, the majority of participants listed themselves as being either not very knowledgeable or somewhat knowledgeable, with only a handful being very knowledgeable in machine learning techniques. It's worth noting that we did have no responses of extremely knowledgeable in machine learning, including from the developers who were participating in the experiment to test their own machine learning models. So I thought that was kind of interesting that even the machine learning experts did not classify themselves as being extremely knowledgeable in machine learning. So the first question we asked in the survey was for the participants to estimate how often they utilize probabilistic forecast products as part of their work-related duties. The purpose of this question was to gauge how much experience the participants have with probabilistic forecast products, and to provide greater context for later questions in the survey. For the purposes of this research, probabilistic forecasts were defined as any probabilistic guidance derived from another model or ensemble, which helps represent the inherent uncertainty and spread often associated with models, especially deterministic models. For example, probabilistic forecasts often extract information not explicitly provided by the original model. We broke down the results between those who identified themselves as forecasters and those who identified themselves as researchers. You can see that the forecasters all generally said that they utilize probabilistic forecast guidance on a daily basis or at least several times a week, whereas researcher experience utilizing probabilistic forecast guidance as part of their work-related duties was more varied. All right, the next question asked the participants to consider a probabilistic forecast product that they have utilized in the past. And then when evaluating how useful that product might have been to their personal forecasting process, how important were each of a series of factors to their decision-making process. So this figure on the left here shows a kernel density curve representing the responses to each of the factors that we presented the participants. And the dashed lines here indicate the average importance score, where a score of 0 represents a not at all important metric, and a score of 5 represents the factor being extremely important. So we're going to start down here at the bottom just to keep the suspense up a little bit longer. So we'll just step through each of these. So the first, the least important, according to the participants, was their previous experience with the developers of the product. So this indicates, do they know the people making the product? Have they worked with them in the past? Things of that nature. The next least important factor was previous experience evaluating experimental versions of the product. Next on the list, we have how closely the probabilistic output aligns with human-generated forecasts. This is kind of going back to what Amanda was talking about in her presentation, where sometimes the outputs from, say, a machine learning model, for example, doesn't necessarily match what a human would produce. Moving on up the list, we have use by other experts in the field. How closely the variables used as input to the product align with traditional meteorological knowledge. Knowledge of how the probabilistic output is derived. And performance of the product in case studies comes in at the fourth most important factor. Moving into the top three, we have the statistical verification of the product at number 3. Timeliness and availability of the product ranks as the number 2 most important factor. And finally, knowledge of the product's limitations and possible failure conditions is listed as the number 1 most important factor that both forecasters and researchers consider when evaluating how useful a probabilistic product might be for their personal forecasting process. All right, the next question was very similar. This time we asked them to consider a new probabilistic forecast product that is explicitly the result of a machine learning model. And then we asked them to re-rank each of the factors and how useful they might be when determining how important the product could be for your forecasting process. So this is the exact same question, except this time we're telling them explicitly that they're evaluating a machine learning model. And you can see right away that there's actually very little difference from the previous slide. The only real changes is the statistical verification of the product moved up 1 spot over timeliness, and how closely the probabilistic output aligns to human generating forecasts moved up over use by other experts in the field. But overall, participants showed very little discrimination in how they ranked factors between any probabilistic guidance and explicitly machine learning guidance, other than, again, that slight increase in the emphasis on model verification for machine learning. And you can see this more clearly if I overlay the kernel density curves, the figure on the left here. This time, probabilistic guidance, any probabilistic guidance is indicated by green, and machine learning specifically is indicated by orange or yellow. And so once again, you can see there's very little differences in the distributions of the responses between those 2 questions. Now, this might seem like a rather anticlimactic result. However, this is actually a very important thing for us to consider as we move forward with the machine learning community and how it might relate to operations. For example, granted, these are, it's a small sample size and it's very early indications, but this could potentially indicate that forecasters in the operational community are either they do not have or they are not willing to admit that they have an explicit bias when identifying or when evaluating machine learning guidance over other probabilistic products. Now, things do get a bit more interesting, however, when we break down the results between forecasters versus researchers. So this is going back to the question that asked about any probabilistic guidance, not the machine learning question specifically. And again, with the same layout of figures here. This time, forecasters are indicated by blue, researchers are indicated by red, and the factors on the left here are ordered by what forecasters consider to be the most important. And you'll notice right away there's actually a pretty large discrepancy between what the forecasters and the researchers consider to be important in the #1 spot, and that is timeliness and availability of the product. This is what forecasters said is the #1 most important factor that they consider when evaluating the usefulness of a new forecast product. And there's almost a full step difference, a full 1-point difference between the forecasters and the researchers for this particular factor. So hold on to that. We'll come back to that here in just a minute. A few other differences down here at the bottom. Forecasters ranked how closely the variables used as input to the product align with traditional meteorological knowledge higher than the forecasters. Same with the use by other experts in the field. And if we look down here on the very last one here, previous experience with developers of the product, although the averages themselves were fairly close together, if you'll notice the distributions actually show an interesting dichotomy between the forecasters and the researchers, where forecasters are indicating that they do consider previous experience with developers more so than researchers would. And so this is an interesting point to consider moving forward, and something to keep in mind that we as developers do need to be in communication and collaboration with the forecasters we're developing for in order for them to gain that experience with us as developers. So here's the same results, this time for the question that explicitly asked about machine learning guidance. And there's not really many differences here from the previous slide, other than the difference and the importance that the two groups ranked, timeliness and availability, has actually increased somewhat. And the forecasters ranking stayed pretty consistent, but the researchers actually reduced how important timeliness and availability is for machine learning guidance versus other probabilistic guidance. So this bears the question, why product timeliness? We as developers live in a world where success is measured in how well our models verify. Why in the world would forecasters put the timeliness of the product over the verification of the product? And the simple answer to this is just the reality that operational products tend to have strict time deadlines. Guidance must arrive early enough for forecasters to actually look at it and process the information it's providing in order for them to incorporate it into their forecast process. And any guidance that arrives after the deadline of the product is not going to be able to be utilized for the issuance of that product. Furthermore, forecasters tend to set up procedures or presets, essentially, that allow them to streamline their forecast process. But in order for the forecasters to make the conscious decision to add some new guidance to their forecast process or their procedures, the guidance must be available to them reliably and in a timely fashion. So one example of this is the href calibrated thunder guidance, which I helped design in order to help Storm Prediction Center forecasters better predict where thunderstorms will occur within a 24-hour period. Now, the 12Z href, for the high resolution ensemble forecast, begins to come into the Storm Prediction Center at about 1400Z. The Storm Prediction Center's day 1 convective outlook is due by 1630Z, and forecasters generally start working on the product by about 1430Z. Now, forecasters require about an hour, sometimes longer, to process, digest, and evaluate the guidance, make any necessary changes to the product, conduct the product creation, and perform an internal quality control process. This means that in order for the href calibrated thunder guidance to be utilized in the creation of the day 1 outlook, it needs to arrive to the forecasters no later than 1530Z. So this means that we have about an hour-and-a-half window to read in 10 ensemble members from the href, convert them from a 3-kilometer grid to a 40-kilometer grid, apply the algorithm to that data, and process that data into a format that the Storm Prediction Center forecasters can utilize. And I can tell you from personal experience, that was not an easy window to meet. I ended up spending probably twice the amount of time actually trying to optimize the code to make it fit in that time window than it did actually developing the guidance in the first place. So this brings us to the next question of the survey, which says, when developing a new probabilistic forecast product intended for operational use, how important is it for developers to collaborate with operational forecasters during each of the following steps? These results were fairly similar between both forecasters and researchers, so I'll just show the bulk results here. Product testing was ranked as the #1 most important step to collaborate with forecasters, followed by publication, training, and outreach, with a specific emphasis on the training aspect. Next up, we have the initial design and planning of the guidance, followed by exploratory research, and finally, technical and logistical development was ranked as the least important for collaboration with forecasters. So here's a few open response comments that we got from several of the forecasters participating in the survey. In the interest of time, I'm not going to read through these, but if you go back and watch the video later, feel free to pause and read through these. There are actually some pretty interesting insights here. And so after reviewing the results of the survey, collaborating with Storm Prediction Center forecasters, as well as Storm Prediction Center management, and considering my own personal experience in transitioning research products into operations, I have created a list of recommendations here for anyone looking to develop some new product for operational implementation. And I know that the theme this week is machine learning, but these recommendations actually apply pretty well to any guidance intended for operational use. So the first recommendation is to communicate with your end users early and often. Find out what are their operational needs, as well as what are their technical requirements. You might be surprised to find out several operational centers within the National Weather Service have only recently added Python as an operational programming language. Beforehand, they primarily relied on C languages, as well as Fortran and older languages like that. Next up, program with timeliness in mind. Find out early on how much time your code will have to run, and then make it fit within that window as you develop. Use good programming coding practices, and try to optimize your code as you go to save yourself a lot of headache later on. Focus on individual cases and case studies just as much as bulk statistics. It's one thing to say that your model has a POD of 0.7 and a false alarm rate of 0.1. Forecasters want to know when the product works and when it doesn't. Will the product work in this exact situation, or should I throw it out of my forecast? Be able to explain to the forecasters how a product works and why it may fail in some situations. Next up, consult with domain experts whenever possible. Don't try to reinvent the wheel. Any new guidance that you provide should be novel or exceed the quality and skill of similar existing products. And also try to stay consistent with domain knowledge and standards. If the forecasters are used to looking at wind speed and knots, make sure that your model produces wind speed and knots and not something else. And finally, give your end users plenty of time to test and experiment with a prototype before it goes operational. Provide the prototype to the forecasters or to your end users in their native software, or provide a clean, intuitive interface that they can use without a whole lot of hassle. Also provide an easy way for them to submit feedback, bug reports, and questions to the developers, and be responsive whenever they contact you. Make experimental products timely and consistently available over the full intended domain, and specifically make your prototype as close to operational as possible. So for example, if your prototype is intended, or if your final version is expected to cover the entire CONUS, the prototype should as well. If the full operational version is expected to run twice a day at 14Z and 2Z, for example, the prototype should as well. And then finally, provide your end users with training for all experimental products. Now, I know it can be a bit challenging to do this, especially when you're still in the prototype stage and things are changing and things are being updated. But the more information you give your end users, even while they're testing the product, the better feedback that you'll get, and the more trust that they will have in the outcome or the output from the guidance. So that's all that I have. I'll be glad to take any questions now. And if we don't get to them today, you can email me at david.harrison@noaa.gov. Thank you.
You have 2 over on Slido.
All right, so Amanda asks, interesting talk. Is the overlap between participants, being both forecasters and researchers, taken into account the differences between what they find important? Is the overlap between participants, being both forecasters and researchers, taken into account the differences between what they find? Yes. So as I mentioned early on, there were some participants identified themselves as both researchers and forecasters. Their responses were included in both categories when I split it into forecasters versus researchers. So their opinions are being applied to both categories in that situation. Move on to the next one. How often are you planning to conduct this type of survey to establish the trust factors, as we all are at the starting point in accepting AI and ML techniques? That's a very good question. And there's already plans to include this survey again in next year's hazardous weather test bed. We're also looking to possibly expand the survey to go out to maybe more National Weather Service forecast offices and survey more of the Storm Prediction Center forecasters who were not included during the HWT this year.
I would add one more thing to that, and that is that Julie and Ann are also doing in-depth surveys with the forecasters. Those are starting. Julie and Ann can pop on and tell me when they're starting. I think they start sometime this summer.
Yes, they do. A couple things. So yeah, we're actually doing a pretest this afternoon because we want to pretest the interview guide. We'll do a few more, and then we'll be starting the interviews like hopefully in the next week or two. But I think what David's doing here, and if there's some opportunity to collect this data broadly, because it's a nice, short, succinct survey, we'll complement it well. And then we'll move on to doing the experiments and other interviews. I think NOAA generally was also thinking about doing a broad like AI survey. And Amy, you might remember this better than I do. So, but I really think that the way that David constructed these questions, because they touch on some of these features that we know from the literature are really important, is probably yielding really good data.
There was a survey from the NOAA AI Center, but I don't know if it's done or who has the, I mean, presumably they have the results. You have more questions showing up, David, I'll stop.
Okay. Someone says, excellent presentation, thank you. Knowledge of the product's limitations and possible failure conditions, timeliness and availability of product testing are all good, but what about the availability of data by forecasters for AI model developers to train their models for perfection? So I believe your question is asking how important it is to include human-generated forecasts or when training or comparing AI models. Is that correct? If that's the case, then I would say it's very important as well to, as developers, that we consider, not only what are the forecasters producing already, but how they're doing it, what type of output, how does their output compare to artificial intelligence output and things of that nature. So yes, it is very important to have data from the forecasters available for us to train on. Something
that to also mean that we need data in general, but maybe I misread, because we do in general, NOAA needs to save a lot more data than they're already saving, but I think that's preaching to the choir here.
Yes. All right, next question. I guess we still have time. Looks like developing prototypes is the best way to enter the field. Two contests have been mentioned so far, the NOAA Hazardous Weather Testbed and the Subseasonal Seasonal Predictions Challenge. What other places can a developer go to get feedback from forecasters? My recommendation, if you are not able to, or you're not ready perhaps to submit guidance to the NOAA Hazardous Weather Testbed or some other NOAA-based proving ground, just reach out to your local forecast office. Reach out to various research centers within NOAA, the National Institute for Storms Laboratory. The Storm Prediction Center is an operational center you can reach out to. These operational centers may not always have time to really dig into brand new guidance that hasn't been thoroughly tested yet. But if you have questions in general about what are their needs, what are the timeframes that they're looking for, things of that nature, I'm sure a lot of these operational centers would be happy to discuss those with you.
I think you have time for one more question.
Okay. Let's see. I think that's a comment on a previous question. Have you considered splitting the research among researchers and managers? How do the managers see operation of AI-based products? That is a very good suggestion and something that I'll be looking towards in the future. One comment on that is most of the management at the Storm Prediction Center are also forecasters. For example, our morning coordination meteorologist is also a fill-in meteorologist who fills in shifts whenever the main forecaster is on vacation or not available for some reason. Same with the science support branch chief, as well as our science and support officer. So a lot of the management are also forecasters in their own right and have been full-time forecasters in the past.
And with that, I think it's time to shift to the next talk. So if Ryan or Randy can share slides.
Okay. Hello, everyone. I'm Randy Chase. I'm a postdoc working for Dr. Amy McGovern as part of the TAI4ES Institute. Ryan, you want to unmute and introduce yourself?
Sure. Hey, everyone. I'm Ryan Lagerquist, and I'm a research scientist at CIRA and the NOAA Global Systems Laboratory, or GSL.
So we're joint presenting today, mainly based off of Ryan's PhD work, and we're trying to give a concrete example of how you can use XAI techniques to help, tease out some extra trust from your model, and not only just with forecasters, but other researchers or reviewers who are reading your papers. So that's kind of the focus for today. Specifically, the motivation behind the machine learning aspect is that tornadoes are way too small to be explicitly resolved by our operational numerical weather prediction. And, of course, models are getting better and better and have higher resolutions, but for the meantime, we're stuck to kind of using these proxies, and hopefully machine learning can provide and fill in this gap in the meantime. There are many new data sets out there, including, the GOES imagery, which are high resolution in both space and time, as well as our dual polarization radar network in the United States. But these fields are not necessarily easy to assimilate into our numerical weather prediction. Furthermore, the retrievals from these products have lots of uncertainty, so these uncertainties can propagate through our weather prediction as well. So that's kind of why we're using this machine learning approach to help predict in short-term forecasting of tornadoes. So just as the example for our tornado prediction, Ryan's paper, they use a convolutional neural network. Specifically, we're using GridRad as our radar product, as well as the rapid refresh dynamical weather model to give us some thermodynamic and kinematic properties. And then the targets or the labels of our machine learning is the tornado reports from the severe weather data inventory. So we gather each of these data sets. The radar data set gives you where the storm is and some other information about, how is the storm already spinning? Is there any convergence or divergence associated with the storm? And like I said, the RAP gives us some sort of thermodynamic information of how the storm could evolve. And then the tornado reports are, yes, there was a tornado in the next hour, or no, there was no tornado in the next hour. And if you want more specific details than what we're providing here, please look at Ryan's paper in WAF. It goes into a lot of detail to explain the little intricacies of the data processing. So just a quick overview of the radar data. GridRad is a method of making this mosaic across all of the weather radars in the United States. So you can see here, we're not evenly spaced among these radars. So ideally, we would like them on one common geometric grid. So GridRad does this by combining things into a 5-minute time step interval. It has approximately a 2-kilometer horizontal resolution. There's a 0.5 kilometer vertical resolution for the first 7 kilometers, but then it switches to a 1 kilometer resolution aloft above that. And in total, there's 154 days in this database of images where we're using 2012 to 2014 for training. Validation, so your hyperparameter tuning and whatnot is happening on 2015 through 2018, and then testing is occurring on 2011. Getting a bit more on the specifics of what actually is being used as inputs to the machine learning. So there are storm-centered radar images. So here's just an example from the data sets. The top panel in the rainbow color bar is the reflectivity. We're only showing select heights here, but there are the full heights involved in this process. There's also the spectrum width, or you can think about this, the standard deviation of the Doppler velocity. So this is a proxy for, turbulence within the radar gate. So that's included at all heights, as well as we also have kinematic fields that were derived from the Doppler velocity measurements, such as vorticity and divergence. So you could see that these storm-centered images would have just as much perspective as a human would if you're just tracking these storms. So say as a forecaster looking at AWIPS, or if you're just a storm chaser out in the field looking at your radar scope, you can look at these type of storm-centered images to gain information of, will this storm produce a tornado in the next hour? To actually get these storm-centered images, there takes a bit of effort to track where the storms are going and where they've been. So again, we refer you to the 2020 paper, but essentially we track these 40 dBz echotops, which is a common parameter for tracking convective cells. And then we track them over time, and eventually we create these storm-centered images that now have, one picture with all those variables, but we could also look at different times in its evolution prior to tornado genesis and also feed those in as predictors. There is some effort to make sure that these are all oriented in a similar manner. So using the RAP measurements, we can rotate them so that they have the storm motion to the right. And because we track where explicitly the storms are moving, you can also orient the images to the right as well. To get the proximity sounding, instead of giving a 2D field for now, it's just one sounding from the RAP data. And we use, I think it's about a half hour into the future of from the current storm location as the thermodynamic environment that it's headed towards. Then we link the storm and the sounding to any nearby tornado reports. And we'd say, well, if there was a tornado report within a certain distance of this image in the next hour, then we say, yes, this storm went on to create a tornado, otherwise no. So this is our binary classification. So we're using convolutional neural nets because there is a lot of spatial features in these radar images. So I think most people are familiar with a hook echo, and this is predominantly associated with supercells, which often lead or are more likely to lead to tornadoes in the future. So we would like to encode that information into the machine learning process and give it all of the potential you possibly can to help the model perform well. So that's what we're doing here. There's convolutions, and then there are pooling layers that decrease the spatial resolution so you can get a more wide perspective of the larger scale patterns. And then also the end is a fully connected layer to either output yes tornado or no tornado. And specifically, the activation function here is scaled so that it is a probability, so that the machine learning model can say, hey, I'm 70% confident that this this image will lead to a tornado, while I'm 30% not confident that it won't, type of perspective. So just some results, so that way you have some faith that the model has skill. So before just jumping into the XAI, it doesn't really make any sense to apply these interpretation or explanation methods to a model that has no skill, right? So if I'm interpreting a model that can't predict tornadoes, then it doesn't tell me anything if I'm not going to use that model in the end anyway. So here's some results from his paper. So these are the rock curve and the performance diagram. Generally, if you have an area under the curve greater than 0.9, that's excellent performance. But just keep in mind that this is a very lopsided testing data set, because obviously tornadoes are rare events. So that's why this score is probably a little higher. That's why you also look at other metrics to determine your skill, such as the CSI, which might be a little low, 0.3. But again, these are difficult instances to predict. But the end takeaway here, if you're not familiar with these diagrams, are that the model does show skill. So there is, the machine learning has learned something and is able to predict with some skill if a tornado will occur or not. But as we've talked about earlier in some of these discussions, just showing these bulk statistics, especially even myself, I'm not necessarily satisfied with just looking at how it performs on a data set that I created. I would actually like to know, dig into a couple examples, or what we'll show in the future here is if we can dig into what the actual machine learning is deciding why it's saying this is going to create a tornado or not. So one example of why we might want to look into this, this is a great example where they trained a classifier to say, is there a horse in this image or is there not a horse in this image? So originally they trained these images, and it turns out that all of the horse images had this label on the bottom left. So it turns out that the machine learning model said, hey, I know when it's a horse in this image because all of them have this label in the bottom left corner. So that's what the XAI technique here is highlighting. It's, hey, look, there's writing down here, it's a horse. And when you remove that text, it says no horse. So this is just a common problem, that you want to make sure your machine learning is predicting things for the right reasons. And we don't necessarily want our machine learning model saying, hey, there's going to be a tornado here because we have all the data, right? We want to say there's going to be a tornado here because this supercell shows characteristics of supercells that create tornadoes in the future. That's the better answer we would like. So that's what we're going to try to tease out with some of these XAI techniques. So Ryan, you want to take over from here?
Sure, thanks, Randy. So I'm going to talk about 4 different XAI methods today and how they were applied to the tornado prediction problem, and also how I used either significance testing or physical constraints to ensure that the outputs of the different XAI methods were robust instead of the XAI methods just reflecting noise. So a good analogy for the people who are more traditional statisticians instead of machine learning people is that when you do principal component analysis, or PCA, if you apply PCA to completely random data and then look at the top principal components you get out and look at the spatial patterns inside those principal components, you see a north-south dipole and an east-west dipole and some tripole patterns and some quadrupole patterns. And if you were not being careful, you could easily convince yourself that these patterns represent something physical, even though they come from completely random data. And XAI methods can do similar things. So that's why we did some significance testing here to ensure that the results coming out of the XAI methods were significant, and then ignore the noise. So the first method is called the permutation test. The permutation test measures the overall importance of each predictor variable. In our case, there were the 4 radar variables that Randy showed you, and then 5 sounding variables as well from that proximity sounding. When I say overall, I mean averaged over all the testing examples, over all the storms in the testing set. And this is a method, actually every single XAI method that I'm presenting here is applied to the trained CNN. So none of these XAI methods involve retraining the CNN. So they're quite computationally efficient. The importance of a predictor variable x sub j is measured by how much the CNN performance declines when you permute or shuffle the values of x sub j. And that just means, for example, if x sub j is reflectivity, you randomly shuffle the reflectivity maps around so that they're all assigned to the wrong examples, but they remain spatially intact. So you just take the reflectivity map from storm A, and maybe that ends up getting assigned to storm D, and the reflectivity from storm D ends up getting assigned to storm C, et cetera, et cetera. If you do that shuffling procedure and the performance of the model declines significantly, you can conclude that reflectivity is an important predictor variable. If the performance doesn't decline significantly when you randomly shuffle all the reflectivity maps, you have to conclude that either reflectivity is unimportant, or maybe reflectivity is just too strongly correlated with the other predictors that aren't shuffled. Next slide. So there's 4 different versions of the permutation test. I'm not going to spend too much time laboring over the differences among the 4 versions. I've given talks on this before, including in the Explainable AI short course that was run through TAI4ES that just ended a few weeks ago. So if you want to learn about the nitty-gritty details of all 4 versions of the permutation test, you can go back there and look at that material. There's a link to it on the front page of AI4ES.org. I think it's still there anyways. So the 4 versions of the permutation test are the single pass forward test, the multi-pass forward test, the single pass backwards test, and the multi-pass backwards test. The whole point of running 4 different versions of the test is that if you have pairs of strongly correlated predictors, the 4 versions of the test will give you somewhat different results. If the predictors are uncorrelated, the 4 versions of the test should give you similar results. So we found benefit in running all 4 versions of the permutation test and then looking at the results that were consistent across the 4 versions of the test. Next slide. So like I said, I'm not going to labor over the 4 different versions of the permutation test. So I'll dwell on this slide for maybe half a minute and then skip over the next few. So that will be stuff people can go back and look at later if they would like. So this GIF is showing what happens in the single pass forward permutation test. So if you look at the Each column here in the green is representing one predictor variable, and then each row is representing one example or one storm. So you go through the data set, you just loop over all the predictor variables, and you see what happens when you shuffle the values of that predictor variable and just randomly assign them to the wrong examples. So in this case, the predictors are reflectivity, vorticity, spectrum width, divergence, and then the 5 sounding variables, which are U wind, V wind, virtual potential temperature, relative humidity, and specific humidity. So in this case, there's 9 predictors instead of 6. But this GIF just shows you what happens. You never permute the values of the labels. Those are the 0s and 1s indicating which storms are tornadic and non-tornadic in the next hour. At each step of this test, you just randomly shuffle up the values of one predictor variable, run that new data set through the model, and then figure out what the new loss or the new error of the model is. So next slide, Randy. I'll probably get you to skip through. Yeah, next slide again. Okay, perfect. So this slide is showing results. The radar variables are shown with the orange bars, and the sounding variables are shown with the purple bars. So again, there's 5 variables from the proximity sounding and 4 from the radar image. And each one of these panels is showing a different version of the permutation test. In each panel, the most important predictor is at the top and the least important is at the bottom. So if you want to just see the few most important predictors, just read the top few bars. And if a variable is in bold font, that means it's significantly more important than the variable below it. And that's determined by a bootstrapping test with 95% confidence level. So just looking at the results that are consistent across all 4 versions of the permutation test, reflectivity and vorticity are the 2 most important predictor variables according to all 4 versions of the test. And then V-wind is the most important sounding variable according to all 4 versions of the test, although in only 2 of those 4 versions is the importance of V-wind statistically significant compared to the next predictor below it. The reason that V-wind, or the north-south component of the wind, shows up as being so important is likely that wind shear is important for mesocyclogenesis and tornadogenesis. And you can determine at least part of the wind shear by looking at the vertical profile of V-wind, which is one of the 2 wind components. So next slide, Randy. Okay, so this is the second XAI method. So another method of gaining trust with a machine learning model is to analyze how it performs on the extremes within your testing set. And here we can gain valuable information by considering both the best hits and the worst misses. So the 100 best hits are the 100 most confident hits. These are the 100 storms that actually produced a tornado where the CNN gave it the highest probability of producing a tornado. And then the 100 worst misses are the 100 most confident misses. So these are the 100 storms that produced a tornado with the lowest forecast probabilities from the CNN. So some questions that you can consider when analyzing these extreme cases. 1 is, do the input examples have any obvious commonalities? And 2 is, can I find a meteorological reason why these cases would be particularly easy or difficult? Next slide. So here, I'm not showing any sort of XAI map yet. I'm just showing you what the storms themselves look like, or what the input variables for the storms look like. So here is a composite radar image for the 100 best hits. These are the positive cases, or the tornadic storms with the highest forecast CNN probabilities, average of 99.2% forecast probabilities. So the CNN did really well predicting that these storms would produce tornadoes. And you can see some supercellular features in this composite of 100 storms, which the arrows are pointing to down below. So you can see a hook echo, you can see strong low-level convergence, you can see strong upper-level divergence, you can see a deep reflectivity core with values up to 50 dBz, even at 10 kilometers above ground level. And you can see a deep mesocyclone with strong rotation or high values of positive vorticity. Next slide. This slide is showing the worst misses. So these are the tornadic storms where the CNN had the lowest forecast probabilities. Its average probability was only 8.6% for these 100 storms. And in the composite, you can see these storms look very different than the best hits. So the best hits, that composite looked very supercellular, and I looked at all the 100 individual storms, and every single one of the 100 storms look like supercells. In this case, for the worst misses, the storms have weak rotation and they have a shallow elongated reflectivity core. So they look like part of a quasi-linear convective system. And I did an inspection of all these 100 storms individually and concluded that 67 of the 100 storms are part of a quasi-linear convective system, or QLCS. QLCS storms generally produce weaker tornadoes, and these tornadoes are commonly missed by humans and other forecasting methods, including apparently our machine learning. So next slide. Okay, so the third XAI method is saliency maps. Saliency, which some people call sensitivity, is just defined by this linearized partial derivative. So it's di p di x linearized around x naught. So p is the forecast tornado probability, x is one of the predictor variables, and then x naught is the predictor variable that occurs in a true storm. So in plain English, saliency is a linear approximation to this partial derivative of tornado probability with respect to the input variable, valid around the input variable that you find in a real example or a real storm. So our saliency maps are answering this question at the bottom. We're asking the CNN, how would you change the storm to increase or decrease its tornado probability? So next slide. So here is the average saliency map for the best hits. The composite storm in the background, you've already seen all those color maps of reflectivity, vorticity, and spectrum width. The only thing that's different here is you're seeing contours on top representing the composite saliency map for these 100 storms. The solid contours mean that there's positive saliency. So that means tornado probability increases when you increase the value inside a solid contour, whereas tornado probability decreases if you increase the value inside a dashed contour. So it's telling you where you want to increase or decrease the predictor value to increase tornado probability. So these arrows are showing the main patterns that show up in this composite image over 100 storms. Tornado probability increases with vorticity inside the mesocyclone, especially at lower levels, more than at the upper levels. Tornado probability increases with spectrum width, and it increases with reflectivity inside the reflectivity core, more so at the upper levels than at the lower levels. Next slide. Here is the average saliency map for the worst misses. Again, a composite over 100 storms. Basically, what you can see here is that tornado probability increases with all variables inside the storm and around the reflectivity core, as shown by those really dark solid contours. And then around the reflectivity core, you see really dark dashed contours, meaning that saliency is negative. So tornado probability increases as all those variables decrease around the edge of the storm. So basically, tornado probability increases as the storm becomes stronger, but also more discrete or isolated from storms surrounding it. That's what the dash contours around the edge of the image are telling you. You want the storm to be more discrete or isolated from other convection. You don't want other reflectivity around this storm if you want it to produce a tornado. So next slide. So I won't have too much time to talk about the significance tests, but I will do it here for saliency maps. So to ensure that the saliency maps are reflecting actual meaningful physical relationships and not noise, we applied these 3 sanity checks proposed by a paper by Adebayo et al. In 2019. The paper is called Sanity Checks for Saliency Maps. They came up with 3 sanity checks called the edge detector test, model parameter randomization test, and data randomization test. So basically, they were figuring out if some really simple methods other than the trained model could reproduce the saliency maps from the trained model. And if you can reproduce saliency maps or any other sort of XAI heat map with a simple method, like just an untrained edge detector, then the saliency maps from the trained model probably don't mean much. You're not really discovering anything with the trained model if you can reproduce the XAI heat maps with something else that's not even trained. So we did something a little bit beyond the original Adebayo paper. The sanity checks in the original paper were all visual, but we've included a formal significance test based on Monte Carlo resampling. You can read the details of that in chapter 7 of my dissertation, as well as an upcoming paper, hopefully, that's still under review. So next slide. Okay, so here I'm showing the sanity checks for the best hits. So panel A is what you've already seen. That's the composite saliency map for the 100 best hits. Panel B is a saliency map from the edge detector. Panel C is the saliency map from the data randomization test. And panel D is a saliency map from the same convolutional neural net as in panel A, but I shuffled the weights in one of the convolutional layers. So you can see visually that the 4 sets of saliency maps are quite different. And also I put stippling in the background where the differences are statistically significant. So the percentage of significant differences for these dummy saliency maps is always around 20%, 20% in panel B, 23% in panel C, and 16% in panel D. So the big takeaway only 20% of the differences are statistically significant. So saliency maps created by the trained CNN may not be super informative. So next slide, Randy. I'll get you, can you skip ahead to the sanity checks for the, actually, you know what? Yeah, skip ahead to the sanity checks for the class activation maps. I'll show those real quick and then go to the conclusion. Okay, great, thank you. So here I'm showing you the same thing, but this is for class activation maps as opposed to saliency maps. You can see again that visually there's some pretty stark differences between the actual class activation maps in panel A and the dummy versions of the class activation maps in panels B, C, and D. And also, according to our significance test, many more of the differences here are statistically significant, anywhere between 66 and 81% of the grid points. So the takeaway here is that the class activation maps created by this trained CNN are much more informative than the saliency maps because they're much more difficult to recreate with just a dummy method. So with class activation maps being an attribution method and saliency maps being a sensitivity method, this may indicate that generally attribution methods are give you patterns that are more significant than sensitivity methods, but that needs more investigation in the future. Can you go to the conclusions, Randy? So we'll have to skip over backwards optimization, but I think I've covered the most interesting parts of this presentation. Would you like to read the conclusions, Randy?
Sure. Okay. So there's obviously many more techniques out there, but I hope that this discussion has fostered some thoughts on your own behalf of whoever is working on machine learning these days, that, you know, beyond just looking at the statistics or beyond looking at one specific case study that you think your method worked really well, I think these are complementary techniques that help you, you know, analyze and gain confidence as well as trust in your machine learning method. So, you know, the main findings from these XI methods, you know, that these are generally consistent with meteorology. So the best performance were for the easy examples. So, I mean, most bachelor's level meteorologists know what a hook echo is and would say, yeah, hook echoes are generally something that is easier to forecast than a quasi-linear system. The most important part of the storm, as indicated by the cams, were the right rear flank, you know, where the tornado is expected to be or will be in the future. And again, tornadoes were more likely for discrete storms. So we hope that you agree, going through this analysis, that now at the end of the discussion, you are a bit more trusting of the machine learning methods, that it agrees with known meteorological type things. It's not just doing random, you know, we're picking this image leading to a tornado because it had a label on it. You know, it's learning some physical processes as well. So now we'll open it up to questions. I apologize that we went over and didn't get to cover all the slides, but I'm sure these slides will be published live too, so somewhere. Ryan, do you want to cover that first question?
Yeah. Yeah, the reason we tested our data set was 2011 to 2018, and we made the testing set 2011, is that we had two radar data sets. We had one called MIRS and one called GridRad, and 2011 was the only year that the two data sets overlapped, and we wanted to do some apples to apples comparison of the two sets of radar data. So that was why. And thank you for posting that link in the comments, Amy, to the XAI Summer School. I think this question is from me as well. For permutation feature importance, could you permute or shuffle the individual pixels of a feature map instead? Yes, you could. So instead of leaving the map spatially intact, you could also shuffle the maps in space. So you could permute over the grid points and spatially scramble the maps. I haven't tried doing that because that gives you a lot of things to test, because then you'd be testing the importance of every single pixel in the image as well as every variable. And there's 32 by 32 pixels. So there's 1024, and that would just be a lot of numbers to compare. Have I considered applying SHAP? I have considered applying SHAP. I haven't gotten around to it yet, but thank you for that. It's something on my to-do list. So that question was from Francesco Zanetta. I think there's another one for me here at the top. William Keeley, how do these methods of feature importance compare to decision tree methods? Does this allow the CNN to be as interpretable as a decision tree or random forest or gradient boosted forest, etc.? No. The inner workings, I would make a I don't have enough time to talk philosophy here, but I would make a distinction between interpretable and explainable. So an interpretable model is one that's interpretable by its very nature, where the inner workings of the model are understandable by any human. And I would say that's true for a decision tree, maybe not so much for a random forest or gradient boosted forest, because then you're talking about an ensemble of hundreds or thousands of decision trees, where even if you know how an individual one works, it's pretty hard to conceive of hundreds or thousands of them working together. But yeah, a decision tree is an inherently interpretable model, which a convolutional neural network is not, because there's just so many weights and so many things going on inside a CNN. Okay, one at the top here from Raghavendra. I hope I'm pronouncing that properly. It's moving. Labeling is one way to constrain the search and match a pattern, but is object/pattern matching acceptable, or would it make it faster? I'm sorry, I don't understand that question, so I'll have to skip over it. We have one here from Bill. If the RAP profiles have been improving over the years, does that bias the fitting away from the training and testing? Have you tried randomizing the sampling instead of separating by year to see if there's a difference? We haven't. Maybe you can speak to this as well, Randy, since you're now doing the work on this project. But when I initially did this project, I wanted to split the training, validation, and testing data by year to make sure that those 3 data sets were completely temporally independent. I didn't want any leakage or any temporal autocorrelation among the training, validation, and testing data. But I did that with the understanding that yes, the RAP hasn't been a consistent model over the 8 years of that data set from 2011 to 2018. So training on RAP data from 2015 to 2018 or whatever it was, and then testing on RAP data from 2011 could bring up issues because the model configuration has changed over time. Do you want to say anything about that, Randy?
Randy answers, and then we'll declare that the last question.
Yeah, I think this is a problem that a lot of machine learning people in atmospheric science deal with. I mean, our numerical weather prediction are always trying to be improved. So yeah, unfortunately, this is just something we have to be cognizant of, that, you know, parameterizations change, and hopefully things are getting better. So just, I think acknowledging that it exists is good, and you should keep that in mind as you plan these projects. But in terms of having an answer for it, I'm not sure how to limit these autocorrelations in time, you know, like Ryan was describing, versus these improvements in the model. Luckily for the results that Ryan was showing, that most of the information content's coming from the radar data anyway. So that was what the permutation showed, that the reflectivity was the most important feature anyway.
And I'm going to pop in and say thank you, but we're running out of time. We've been doing really, really well at running on time today. So I'm going to hop in and say thank you to everybody, and remind you of what we have. We have 3 more days left to summer school. Hopefully you can see my slides. Tomorrow's focus is going to be on XAI, physics-based AI, and robust AI. Wednesday, we moved to ethical and responsible AI, and we've had some really good questions in the chat that relate to the ethical and responsible AI. I hope we get to all of them on Wednesday as well, but keep coming back. I'm helping to run that day. I'm really looking forward to that day. I'm looking forward to all of it. And then Thursday is on case studies. And so we're going to start tomorrow morning with physics-based AI right away. So we look forward to seeing you at 10 o'clock tomorrow morning. And if you have any feedback about anything that, you know, perhaps didn't go well in the Slido or anything like that, then feel free to send us an email so we can adjust anything for tomorrow. We want things to continue to go smoothly. Thank you.